Shuru, are my slides visible, please?
Yes, sir, your slides are visible.
Do we wait another couple of minutes before we get started, or what
Yes,
should we do?
sir, I think we should wait for few 2 to 3 minutes more.
Okay, sure. So you tell me when to start?
Yes, sir. Yeah. Hello everyone. So today we have our lecture by Professor Mandar Mitra from India Statistical Institute on Information Retrieval, and starts. So we will start now. I hand over to sir.
Surup, please introduce sir.
I just Shuru, did you say I should start now? I'm sorry, I stepped out for a bit.
Oh, okay. Yeah. Yes, sir. Sir, you can start.
So I think one of the earlier speakers also said, those of you who don't have bandwidth problems, maybe if you can turn your video on, it feels less like talking into a black box. Okay, so before we kind of get into the technical details, a quick question. How many of you have already had a course in information retrieval prior to attending this winter school? You can either do a raise hand or just unmute your mic and say yes.
No, sir.
You had. Okay. Okay, I don't see any raised hands at all. So, I mean, am I right in assuming that nobody here has done a course in IR, right?
Yes, sir.
Okay, sounds fine. So in spite of that, there'll be some overlap because as you might imagine, we're all, all the speakers here are in some way or the other trying to solve language related problems. So in particular, there'll be a little bit of overlap with Tanmoy sir's talk. I'll point it out as we go. So let's get started with this. So basically, I think the other lectures that you've been attending, they are trying to do in some sense, they're trying to address more sophisticated language processing problems. So things like parsing, sentiment analysis, summarization, and so forth. What we will be concerned with for the next 3 sessions is a much more coarse-grained task. It's simply kind of finding a document that's useful for you. So kind of here's the formal problem definition of the most standard task in information retrieval. So you have an information need, and what the system needs to do is it needs to find documents that address that need. So the first point of clarification is I want to distinguish between an information need and a query. So information need is in some sense something that is unstated. It's kind of what's there in your mind. And you as a user convert that into typically a set of keywords. Sometimes it's a kind of well-formed question, but very often it's just a set of keywords. So the information need is what you're really looking for, and the query is its keyword representation. So that's the distinction we'll make between information need and query.
Hello, sir.
And yes, question.
Sir, the screen is blurry. The visualization of the is blurry.
Okay, is that a problem for everybody?
No, sir, it's fine from my side.
No, sir.
No, sir.
Okay, then.
Okay, sir, I will check mine.
Okay, please. The other thing I can do is turn my video off, so that will kind of strain my bandwidth a little less. Okay, let me try that. And then if it still doesn't improve, then I'm afraid it's probably something at your end. Okay, I've just turned my video off, so hopefully the slides are getting a better share of the bandwidth now. Okay, so depending on what kind of information you're looking for, what the system is expected to retrieve could be various different things. And I mean, you just need to think about your searching behavior as ordinary users in order to kind of think about the scope of what it is that we might be looking for. So sometimes you look for pictures, sometimes you look for directions, sometimes you look for maybe movies on YouTube or other kinds of videos on YouTube. So for these 3 hours, we will simply be focusing on text exclusively. So kind of as users, I mean, even without a formal exposure to IR, just as plain users who use a search system every day, many times, what you already know is that, right. So what you already know is that this is the overall kind of schematic behind what we're trying to do. So there's a document collection that's kind of the storehouse or the database or the repository from which you're looking for information from. And you're the user who kind of converts his or her information need into a query and submits it to a retrieval engine or a search engine. And the search engine has done some pre-processing on the document collection. The output of that pre-processing is what we call an index. So the retrieval engine takes your query, consults the index, and gives you back a set of ranked results. So, excuse me. If you look at this overall very simplified picture, the 2 major components that we need to address are this kind of black box that I've called or that I've described as indexing, which is the process of taking a document collection and doing some kind of pre-processing on it so that you build structures that make it easy for you to search. And once this is constructed, how you actually do the retrieval. So let's start with the indexing process. And again, as I said, there'll be a fair amount of overlap with the things that Tanmoy sir has already covered in his lectures. So what we're essentially trying to do is kind of, so here I have a text version of the earlier picture. So we will basically be looking at what kind of processing do you do, what kind of representation do you come up with for documents so that retrieval is easy. That's the first task that we'll address. Once you have the indexed form of a document collection, how exactly does the matching or the ranking or whatever you want to call it, the actual search process, how does that work? And finally, we'll also talk about how you know whether you've done a good job or not. And as a kind of fifth step that's not really mentioned on these slides, but hopefully we will have a chance to look at that issue as well. The question is, suppose you have built a basic indexing and retrieval system, you evaluate it and you get an estimate of how accurate it is. Now, if you want to improve upon it, what are the kinds of techniques that you might employ? So as you can imagine, there are all of the IR community has been working for many decades on improving retrieval quality. So there are lots and lots of different techniques. We look at one of them. So kind of plan is we look at indexing now, basic retrieval methods after this. Then we look at how to figure out how well we've done. And finally, we look at how to kind of improve upon the basic methods that we talk about now. Okay, so first up is the indexing process. And the kind of traditional indexing method that has been used for a very, very long time is what is called the bag of words approach. So in this bag of words approach, again, kind of something that you are familiar with as users, if not as actual kind of system implementers, is that any document or any piece of text for that matter is represented as a list of keywords. So kind of depending on what paper you're reading, different people use different words for kind of the keywords that are used to describe a document. So sometimes they're called keywords, sometimes they're called content descriptors, sometimes they're called terms. So I will also probably end up using these words interchangeably. Mostly keywords and terms. These are the kind of words that I'll probably be using. And all that I mean is I'm basically kind of falling back to your familiarity of what a keyword is. For example, a keyword that's assigned to a technical paper that you might be reading, it tries to give a very high level description of the subject matter of the paper in maybe 3 or 4 keywords. So we're just trying to achieve a more, let's say, complete description of a document than the 3 or 4 keywords that you typically see assigned to a technical article. Okay, so the way we are going to proceed is first we're going to look at how you do this conversion. From given a document, how do you come up with a list of keywords that kind of in some sense describe that document or convey the subject matter of the document? And then we look at, given this list of keywords representation and given a set of keywords as a query, how do you retrieve and rank documents? So the first part, kind of taking a natural language text document and converting it into a list of keywords. This is something, I'm sorry, I'm not sure why I keep going back here. Right. So these are the steps that you use in indexing. And I kind of just looked at Tanmoy sir's slides, and I think several of these he's already talked about, possibly with hands-on. So at least steps 1, 2, and 3, I'll go over quickly. If you need me to repeat anything, just please unmute yourself and tell me so. So first step is kind of just identify the individual words that make up a text document. So this is usually fairly simple. You just look for word delimiters, and that will usually be kind of spaces, punctuation marks, and so forth. Sometimes, of course, tokenization itself happens to be a non-trivial task. So kind of I'll mention, I won't go into any details, but I'll mention two kind of issues related to tokenization. And if you're interested, you could kind of look them up on your own. So the first issue is language specific. So most of the time we deal with languages that are called alphabetic. So you have kind of letters and then you have spaces and punctuation. So it's easy to break a sequence of characters up into individual words. When you come to languages like Chinese, they are not alphabetic languages. So each little complicated looking character there in Chinese could itself be a word. Sometimes you have two such words joined together to make a different word. And the whole idea is that because each little complicated character could be a word in itself, the notion of space is not that important in Chinese. So given a sequence of Chinese characters, it could be hard to identify exactly which subsequences correspond to words. Okay, so I think fair criticism on your part would be kind of, let's worry about English and maybe the Indian languages for now, and we'll worry about Chinese later. So even when you're dealing with that, this is one of the issues that you might have to deal with. So if you're dealing with kind of, say, user assigned tags or hashtags on social media, so something like NLP Winter School is clearly a useful descriptor for whatever we're doing right now. But depending on kind of who's assigned this tag, there might be variations of this. And you really want to break this into NLP, winter, and school separately. So given that it's just a kind of sequence of characters without any space or punctuation in between, there's no obvious way in which you can reliably break such hashtags into their constituent words. But of course, as you might imagine, I mean, it's a the problem is obvious enough. So not surprisingly, people have worked on this. And in fact, if you look on GitHub, you'll find kind of fairly ready-made software which does a reasonable job of breaking up such hashtags into their constituent words. Okay, the other two steps, which again Tanmoy sir has talked about, once you get a list of all the words, you throw out the ones that are stop words, which is kind of, they don't have any, usually don't have a strong connection to the subject matter of the document. So it's no point assigning is, the, of, and such words to kind of describe what a document is about. So you remove them. And finally, you do what's called stemming. So kind of you have inflected forms of words, and usually you want, if the query mentions the keyword resignation, you probably want an occurrence of resigned or resigns in a document to match the user's query. So one easy method is to, well, I won't say easy, but one kind of commonly used method is to reduce all of these words to a common root. So for kind of most of the commonly used languages, certainly for English, you have standard algorithms, and these algorithms usually make use of knowledge about kind of high school grammar, how words in that language are formed and such, come up with a set of rules and implement basically a rule-based algorithm, which, given something like resignation or resign, will convert it into resign. So there are a bunch of alternatives. I mean, if you're dealing with a language that does not already have a ready-made program which does stemming for you, you can explore a number of kind of statistical methods for doing stemming. And a number of them have been proposed over the years. So again, kind of this is usually only one small part of the big pipeline. So kind of I won't spend more time talking about this. Just assume that for whatever language you're dealing with, hopefully there's something that's the equivalent of a Porter stemmer available. Okay, so far what we have, I mean, if you kind of just do a quick half-minute summary of what we've achieved so far. Given a particular document, we've kind of made a list of all the words contained in the document, thrown out words that kind of don't tell you anything about the subject matter of the document, namely the stop words, convert everything else into some kind of a canonical form so that inflected variants of a word, all of them are kind of mapped to the same representation. So far, what we've been dealing with are kind of individual words. But again, kind of your experience, you know that multi-word sequences like computer science, data mining, artificial intelligence, these are very widely used as keywords, essentially because the two words together convey something that is more specific than if you just took the two words together without kind of connecting them as a phrase. So, of course, in order to come up with a good or accurate description of your document, you might want to use phrases also as content descriptors rather than just single words. So then, of course, the question arises, how are you going to kind of identify which, say, word pairs kind of form a valid phrase and which pairs don't. So again, as usual with most problems, there are multiple solutions. One possibility would be to use a part of speech tagger and then kind of maybe you designate certain part of speech sequences as phrases. So something like, say, a string of 2 or 3 nouns, you would call that a phrase. So something like computer science, computer architecture, those would be examples of phrases that would be identified by this pattern. So NN followed by NN is kind of 2 common nouns adjacent to each other. You see this pair, you pick it up as a phrase. Other possibilities, say an adjective followed by a noun. So artificial intelligence would be an example of this kind of a pattern. Artificial is the adjective, intelligence is the noun. Look for patterns like this. Hopefully you'll pick up a number of useful phrases. An altogether simpler method, which turns out to work quite well, is simply based on kind of basically different forms of counting. So basically you look at some statistics related to how often the individual words A and B occur together. And if your statistics, I mean, whatever number you've calculated, if that is in some sense sufficiently significant, then you hypothesize that AB together forms a phrase. So the simplest form, of course, would be to just look at raw counts. So given a large corpus of text, just look at all pairs of words that occur next to each other and count how frequently each pair occurs. And then you just kind of set a thumb rule, like if I see a pair of words occurring next to each other more than, say, 50 times, I pick that up as a phrase. And kind of compared to more sophisticated techniques like part of speech tagging, this simple kind of just frequency counting, at least for the course objective that we have in front of us, which is kind of given a user query, retrieve useful documents, these phrases turn out to work about as well as more sophisticated methods for phrase finding. Kind of one step ahead of this, related but kind of a slightly different problem, is something called named entity recognition. And what named entity recognition is, you could also regard it as a kind of phrase identification, except that named entities usually correspond to things like names of people, say posts like prime minister or chief minister. So they would again be kind of two words, but together they would designate one single entity. You could also be talking about a place. You could be talking about monetary amounts, all kinds of different things. So these multi-word entities, which correspond to, as kind of the name itself suggests, multi-word entities that pertain to or describe a single entity, these are called named entities. And usually kind of, if I, in any of your earlier lectures, or kind of, I don't remember the full schedule, is named entity identification up for discussion? Has it already been discussed? Do you know?
Yes, sir.
Yes, sir.
Okay.
We had it in a hands-on session.
Okay, great. So
Yes, sir.
excellent. So so those could also be like, in addition to the single words that we've kind of obtained so far, you could also have named entities be part of your set of keywords or content descriptors. So once kind of given a collection of documents, you've passed each document through this pipeline of tokenization, stop word elimination, stemming, and phrase identification, possibly named entity identification. What you have is, you've converted your entire document collection into what's called a term document matrix. So you could look at it, you could view it as something like this. Each row corresponds to a single document. Each column represents one keyword. So the entire set of columns taken together basically corresponds to the set of keywords, in some sense a universal set of keywords that you use in order to describe documents in this particular collection. So that's usually briefly referred to as the vocabulary for a particular collection. And to start with, we could simply have, I mean, the entries in the matrix could simply be 0 or 1, signifying presence or absence of, say, term TJ in a document DI. So given this kind of a term document matrix, now our question is, the user's query also consists of a set of keywords, presumably from your vocabulary, otherwise there would be no match. So if the user has provided some set of keywords from your vocabulary, how do you select documents? How do you rank them? So kind of, that's basically what brings us to the question of the retrieval part. So what we've been discussing so far was the indexing part, and next we'll talk about retrieval. So we'll do this in 2 stages. The first easy stage is to kind of figure out which documents match at all. And then the kind of more complicated question is, given that a set of documents have matched my given query, how do I rank those documents in decreasing order of estimated usefulness? So the basic question of whether a document matches or not, that's basically been formalized into what's called the Boolean model. So here your queries look very much like database queries, and you're looking for documents that contain various combinations of words. And the words are typically combined using Boolean operators like and, or, and, not, and so forth. So kind of this is a fairly straightforward problem. And would correspond to, I mean, if you refer back to the matrix I put up, remember you have, so this is what we had. For each keyword here, the corresponding column tells you which documents have that word and which documents don't. So incidentally, as kind of a quick aside, you can easily see that this term document matrix is going to be a sparse matrix. Any individual word is not, I mean, if it's a useful keyword, it's probably not going to be contained in too many documents. Conversely, any single document is unlikely to cover more than a handful of the words in your complete vocabulary. So most of the entries in this matrix would be 0. So kind of just go back to what you learned in your basic data structures and algorithms class. It makes sense to kind of, instead of having a full-fledged N cross M matrix representation for this, it probably makes sense to have some kind of a sparse representation. So one convenient sparse representation is what's called an inverted index, and we'll come to that a little later again. So that's essentially for each TI, which DJs contain that TI. And that's the structure that we are kind of using in our Boolean model here to figure out which documents have matched. So the inverted lists that I talked about look like this. So medicine is contained in, say, D1, D4, D5, D10, and other documents. Hypertension is contained in this particular list of documents. So if you are looking at a query that's medicine and hypertension, you would simply do kind of, you would walk along these two lists, one single pass list merge, and you'd get the intersection. If it's an OR query, you do a union. So kind of way back, kind of all of these, I mean, when the Boolean models were used, they were actually, I mean, kind of, initially they were used in a library setting. So kind of nowadays your kind of the web is basically your default library where you go to look for information. But earlier, when there was kind of far more importance attached to regular brick and mortar libraries and the librarians who staffed those libraries. So if you did not know what book you need to consult, you'd go up to the librarian and say, this is the topic I'm looking for information on. And then the librarian would do a keyword search for you using these kinds of Boolean operators and give you a list of references that you might want to look at. So clearly, I mean, it was a primitive system, and I mean, there are certain obvious disadvantages. There's no ranking. So kind of either something matches your Boolean constraint or it does not. If it matches, then it's as good as any other thing that matches. So kind of, that's not very useful. Plus, the counterintuitive effect of implementing a Boolean system is that suppose you have a query that looks like term 1 or term 2 or term 3 or term 4, and a document has, say, all 4. Compare that to another document that has only term 1. So as far as the Boolean constraint is concerned, the occurrence of T1 alone is as good as the occurrence of T1 and T2 and T3 and T4 if they've been combined with a disjunctive operator. So some of that kind of doesn't gel well with our intuition, which suggests that a term that has a document that has all four terms is probably more likely to be useful. Likewise, think of the converse. You have an AND query, and maybe you have three terms, a document that has none of those three terms. Think of another document that has two out of those three terms. They both look equally bad to a Boolean retrieval system. So kind of in order to address these problems, people came up with what's called the vector space model. So now our matrix is no longer a binary 0-1 matrix. So we are no longer interested in just occurrence or absence. Instead, we want to fill the matrix entries with some numbers that are intended to kind of somehow capture how strongly is, so if you're looking at entry wij, it's going to tell you how strongly keyword tj is related to the subject matter of document di. So of course now, I mean, because you want these numbers, we also need kind of, in order to make this practical, we also need a way to compute these numbers. Again, kind of, even if you haven't been formally exposed to an IR course, you probably, in the course of your reading, you've probably been exposed to the term TF-IDF. So is that correct? Are most of you familiar with TF-IDF as a kind of term?
Yes, sir.
Yes, sir. We know, sir.
Okay, great. Then I don't need to explain what term frequency is, what inverse document frequency is. But from a retrieval point of view, one point that I would like to emphasize is kind of, even though the basic ingredients, namely term frequency, document frequency, and the other thing that's not mentioned in this slide, it's coming in the next slide, that's document length. Even though these three ingredients are kind of commonly known, commonly used, it turns out that the precise arithmetic formulation that you use, which is to say what exact function of TF you are using, that turns out to be vital from a retrieval point of view. So specifically what I mean is kind of what people have learned through experimentation is that don't just use the raw count as the term frequency of or the term frequency component of the weight of a term in a particular document. So don't just use the TF. And why not? Basically, the intuition or what people have observed is that the importance of a function, the importance of a keyword does not grow linearly with its frequency. So if something occurs 4 times versus some word that occurs once, so at that point, you're probably thinking, I mean, just if you just look at the term frequency independent of everything else, you're probably saying that the word that occurs 4 times could be 4 times as important as the word that occurs once. But think of the same ratio a little higher up. So say one word occurs 20 times and another word occurs 80 times. What we expect, and indeed that's what we kind of learn through experiments too, is that something that occurs 80 times is decidedly not 4 times as important as something that occurs 20 times. So kind of once a word has occurred some 20 times in a document is probably very strongly related to the subject matter of the document. So beyond that, an increase in TF is probably not going to contribute to the importance too much. So kind of lesson learned is that don't use just the plain count. If you want to compute the TF-IDF weight of a particular term, use some function that has a sublinear growth. So log is one such. So 1 plus log TF would be, if your TF is 1, 1 plus log TF would also be 1. And thereafter, it would grow slowly compared to just plain TF. And because log has this kind of damping effect, people have also suggested that you could use a double log. So this would kind of damp the growth even further. Yet another variation takes this form, TF by K plus TF. So the difference is between kind of these three is that, well, I mean, the difference between the log type damping and this TF by K plus TF damping is kind of as TF increases, 1 plus log TF or the double log variation, both of them also increase, certainly more slowly than linearly, but they're both going towards infinity. Whereas if you look at TF by K plus TF, then when TF is 0, this is 0, but as TF tends to infinity, this tends to 1. So which means that there's a kind of upper bound that your TF component of the term weight tends to as TF keeps increasing. And kind of not surprisingly, properly used, this last formulation, TF by K plus TF, kind of turns out to work very well in practice. Okay, so the third component that goes up to making a term weight, apart from TF and IDF, is the document length. So essentially, kind of basically, you don't want to retrieve given a particular query, a long document will have a chance of matching that query just because it's long and contains many different words. So you don't want to give that advantage to kind of, in some sense, that's a random advantage. So you don't want to give that advantage to long documents. So kind of you normalize the weight using some notion of the document length. And you could think of the intuition behind this as in a long document, how much of the overall information content is conveyed by any one single keyword. And kind of that would be, usually you expect that to be smaller than the contribution of the same number of occurrences of the same keyword in a shorter document. So what exactly do you use as the document length? Multiple different formulations exist. So you could just use the byte length of the text document. You could look at the number of distinct words in the document and so on. So here are a couple of kind of commonly used variations. One traditional variation, again, cosine normalization, that I'm sure you've all encountered somewhere or the other. You have the TF and the IDF, and together they are kind of for a particular term TI, that's what corresponds to WI. And then you divide by WI squared. So you're essentially reducing all documents to unit vectors. So, I mean, if you think of a document as kind of, remember I started with a picture where the documents were rows in a m-dimensional matrix. So you can basically think of every document as being so what we are essentially doing by cosine normalization is reducing every vector to unit length by dividing by its Euclidean length. Sounds nice from a mathematical point of view that kind of all the vectors that we're dealing with are unit vectors. You can simply take the dot product of two vectors and you would get called the cosine similarity between them. And that's essentially the cosine of the angle between the two vectors. But kind of the mathematical appeal of this formula notwithstanding, kind of in practice, it turns out not to work too well. So kind of one engineering tweak to this notion of how normalization should be done is the pivoted normalization scheme, where essentially kind of don't look at the document length as the Euclidean length of the corresponding document vector. Instead, use the number of distinct terms in the document, and then you use that in this kind of a parameterized combination. So kind of every document gets a default normalization plus some parameter times the number of unique documents, number of unique terms or keywords contained in the document. So kind of the suggestion or the takeaway message from this is that if you have to convert documents into vectors, and especially if you want to use those vectors for retrieval, the basic ingredients remain TF, IDF, and document length. But what precise formula you use for these is going to have a very big impact on how well your retrieval system performs. So kind of one of the so basically, I mean, formulating these different variations of the general TF-IDF normalization scheme is really an engineering task, and kind of over many years, certain variations have turned out to be or have been shown to be more effective than others. Now, these variations could you could just basically come up with these variations based on engineering arguments like the one I gave earlier, or you could kind of build mathematical models for documents and queries, and that would give you a more principled way of obtaining these term weights. But kind of at the end of the day, I would say that I mean, because we are addressing a practical problem, mathematical elegance is probably it's certainly secondary to what works well in practice. So kind of lesson in point is that cosine normalization is nice from a mathematical point of view, turns out not to work that well in practice. So kind of just keep that at the back of your mind, that just because a model is particularly elegant doesn't mean that it's going to do well in practice. Having said that, kind of the next thing that we're going to look at is kind of revisit Tanmoy sir's discussion on language modeling and look at how we use language modeling for kind of this course task of document retrieval. Should we take a quick 5-minute break now before continuing with the language modeling part?
Yes, sir.
Okay, so kind of it's 15:51 by my desktop. So we'll get started at say 15:56 or thereabouts.
Sure, Professor.
So all these slides, I think Shurupendo has already uploaded all these slides on the Google Drive where your course material is being
Yes, sir.
kind of being made available. So I usually find it easier to download them and follow along rather than just depend on what's being shown on the screen. So you can do that. I will get started again, but kind of before I move into language modeling, um, can you quickly provide some feedback about whether it's okay to kind of cover things at the rate at which I'm going, or should I speed up a bit? Or
Sir, it's
Sir,
okay.
it's
Sir,
fine,
it's
sir.
try your going. Yes, sir.
I'm sorry, can you maybe one of you at a time?
Sir, it's okay. It's fine, sir.
Okay. Anybody else thinks
We are
it's
getting the content.
okay? Anybody else thinks I'm too slow, boring, whatever?
No,
It's
sir,
all
the
right to tell
pace is
me, yeah,
right.
yes, this is
No,
very
sir.
boring.
No, sir.
No, sir, the pace is right.
Okay, okay. Um, okay, so I think kind of, so hopefully we'll kind of talk about language modeling for about, I mean, you should be able to finish this in less than half an hour. So as far as I can understand by looking at a little bit of the earlier lecture on language modeling, the objective there was definitely to tackle a harder problem. So the idea was kind of given a sequence of words, you want to predict what word is likely to occur next, or given a sequence of words, given a particular sequence, you want to estimate how likely that is to be a valid sequence in the language under consideration. When we apply language modeling to information retrieval, the ideas are still much the same, but the objective is far simpler. And I'll kind of come to what it is in a moment. So for our purposes, I mean, for the purposes of document ranking, your a language model is just a probability distribution over words. So in fact, again, I'm kind of a number of you have probably already been exposed to the term bag of words, which I mentioned in the earlier session. And you'd have seen that kind of we are disregarding word order altogether. Given a document, we just assign some keywords to tell us what the subject matter of the document is. And we aren't particularly we are concerned about the weights, of course, of those keywords, but we aren't particularly interested in the order in which they occur. That's a kind of a definite difference with the kind of language modeling that you were exposed to, I think, on day 2. So over here, if you kind of relate this to the earlier discussion, what we are really interested in are basically zeroth order Markov processes, in the sense that we are kind of assigning the kind of to each word, or for that matter, to each kind of word and phrase, we are assigning a probability of occurrence that is independent of anything else. So when I talk about, I mean, you could do this. It's basically, as I said, kind of a zeroth order Markov process. You can think of a probability distribution over either words or kind of word sequences of length 1, 2, 3, whatever. So when I talk about bigrams in this context, in the retrieval context, basically kind of don't confuse bigrams here with bigrams in the sequence sense. So I'm not interested in kind of T1 following T2. Rather, I'm just interested in how often do I see T1 and T2 occurring together. So kind of like the phrases that we talked about earlier. So, and once again, kind of just to make sure that you remember what capital M stands for, T1, T2 to TM, this is basically what I described earlier as my vocabulary, or the set of all keywords that are contained in my document collection. So now our objective is, again, kind of same thing as I said before, given a user query consisting of some keywords, you want to find out which document should I rank first, which document should I rank second, and so forth. So essentially, for a particular keyword query, you want to compute a score corresponding to each document. So the way we compute that score, kind of one common method, is called the query likelihood retrieval model. And here the idea is that each document is kind of, or each document corresponds to a language model. Again, for us, that means, remember, it's just a probability distribution over keywords. Now, kind of the underlying thought experiment is that you regard the query as being a sample drawn from a language model. And the principle that you use for ranking is kind of which language model, or equivalently which document, is most likely to have generated the query. So that's basically what you assign to a document as its score. So score DQ is look at the corresponding language model and compute the probability of generating the query from that particular language model. So then I must kind of, for each document, I must say what the language model looks like and what exactly the generation mechanism is. So kind of various different kind of ideas or theories have been used over here. Possibly the most widely used is what's called a multinomial model. So what we do here is we regard each document as kind of a language model, in the sense that, I mean, you can think of it as either a bag containing keywords or equivalently an urn containing balls, where each distinct color or a ball of each color corresponds to one particular word in your vocabulary. So you have a collection of such urns in your document collection. Your user gives you a query consisting of 3 keywords, and then you kind of want to figure out which urn was this particular set of 3 keywords most likely drawn from. And kind of for each document, you work out the probability of generating this particular query, rank the documents in a decreasing order of that probability. So what are we looking at? So this begins to look like a standard probability problem, right? I mean, in each document, you're told that, okay, document D1 has 1 yellow, 2 green, and 1 red ball. D2 has something, DN has something. And now your user has presented you with a sample of balls. And now you want to go back and kind of work out which urn was most likely to have generated this particular query. So kind of if you just use the kind of very familiar balls and urns model and kind of mentally map each urn to a document and each color to a different word in your vocabulary, then you basically, I mean, the user has picked out Q1, Q2 up to Qn, and kind of assuming that you're drawing, I'm kind of weird, assuming that the sampling has been done with replacement. So kind of everything is independent of each other. And so what you get is you simply get a product of each QI given the document language model. So basically what you get is, remember, words could be repeated over here. Not usual. I mean, think of how often you repeat a query keyword in kind of while doing a web search. But in principle, they could be. So the expression that you come up with is if PTI given D is the probability that a word picked at random from D is TI, then basically you take this T given theta D, raise it to the power, however, this TF-TQ, remember, is its term frequency in the query, not in the document. So raise it to its term frequency in the query and multiply over all query terms. Okay, so then all that we have left is, given a particular query, I already know what keywords are contained in the query and how many times each keyword has occurred. So the only thing now that I have to do is to compute or to kind of assign or estimate this particular probability, that given a particular ball, what is the likelihood of drawing a ball of that color from a given urn. So again, kind of just think back to when you did this kind of problem in high school, and kind of you have, so I'll come back to those later on if I have time, but kind of earlier, kind of, or as I said, kind of in high school, we simply deal with what's called the maximum likelihood estimate. So it's simply number of balls of the desired color by the total number of balls in the urn. So this much everybody is familiar with, right? Okay, any questions so far? I think this count by total number of balls in an urn or words in a document, this much I think is already something that kind of your earlier session on language modeling, you kind of came across this idea several times. And in fact, you already know what's coming next. So kind of just quick check. Everything okay so far?
Yes, okay, sir.
Okay,
Yes.
so,
Yes,
so
sir.
you've already seen that kind of the next thing that we are going to talk about is kind of smoothing in order to avoid the zero probability problem. So if a particular kind of translating the zero probability problem to this document retrieval context, what it basically means is, if a query term is missing from a particular document, then this maximum likelihood estimate says that that particular document could never have generated the query. So any document which misses even one of the query keywords automatically gets a score of 0. And kind of that's not a good thing. So kind of you've already seen that there are multiple different smoothing methods. So kind of just because I haven't observed something in my training data, I don't automatically assign it a zero probability. I assign it some non-zero probability based on some principle or the other. So that's what we are going to do here. So first, let's look at, again, something I think that you've already been told earlier, something called linear interpolation. Okay, these things I know you've talked about in detail, additive smoothing and Laplace smoothing, but kind of linear interpolation. You've been told about this, right?
Yes, sir.
Okay.
Yes, sir.
Yes, sir.
So again, I'm kind of the basic idea is the same, but kind of the actual form is slightly different in the sense that when you're doing this for query likelihood estimation, kind of what you pretend is kind of you have another copy of all the balls lying around on the floor. So that's basically your entire collection. And so your experiment now, kind of your user has come up with a set of balls, and the underlying experiment is that the kind of each ball could be picked up from a particular document, or it could be picked up from the floor. So the possibility of getting a particular word here is probability of kind of, if you want to work out how kind of probability with respect or probability of drawing it from a particular document, kind of what you look at is what's the probability that kind of, let's look at the red ball. What's the probability that it was drawn from this particular urn plus what's the probability that it was drawn from the floor? And the probability of kind of picking it up from the floor is the total number of all red balls that occur anywhere in the collection by the total number of words or terms that occur in the collection as a whole. So this is basically, I mean, we're going to use this, I think, in your, I mean, when you were concerned about language model for predicting sequences, and you were trying to do, say, given, I want to estimate Ti given Ti minus 1, Ti minus 2, Ti minus 3. And if you didn't have that, then you kind of went back to Ti given Ti minus 1, Ti minus 2. And if even that failed, then you went back to Ti given Ti minus 1. So you could either do a back off or you could combine all of these. So here we simply, what we do is kind of, this is, as I said, kind of the experiment now is the underlying way that the user constructs the query is the user kind of will pick up a ball either from a document or an urn or from the floor. So the probability of picking a ball of a particular color is now the sum of these two probabilities. So what that kind of gives us is, this is the linear interpolation formula. So lambda is basically a parameter that tells me what is the probability that the user who submitted the query, what is the probability that she picked up the ball from the floor, and 1 minus lambda is the probability that she picked it up from a particular document. So this gives the overall probability of picking up a ball of a certain color from a particular document. So the fancy name given to this linear interpolation formula is the Jelinek-Mercer formula. So kind of if you're looking at kind of papers related to IR, it's more likely that you'll see the abbreviation JM or Jelinek-Mercer used instead of linear interpolation. So just as kind of here, I had changed the background experiment to, as I said, kind of the user picks up a ball from either the floor or a particular document. So the problem with this is that the whatever smoothing you are doing is independent of anything at all. Specifically, it is independent of the document length. So kind of just think about that for a moment. What does your intuition tell you? If you have a large sample and you don't observe a particular event in that sample, compare this scenario with you have only a small sample and you don't observe a particular event in that sample. So if it's a small sample, this is always going to be high, right? So in some sense, kind of the intuition that I'm trying to convey is that if you have a short document, a particular query keyword not occurring in that short document could very well be due to chance. Whereas if you have a long document and the particular query word does not occur in that long document, then that is less likely to be purely due to chance. What does that mean with regard to smoothing? Essentially that if I have a long document, then the probability estimates that I get from a long document are kind of, I expect them to be more reliable and less in need of smoothing. Whereas if it's a short document, then kind of it's a small sample and the probability estimates that I get are probably inaccurate. So a short document, the weights should be smoothed to a greater extent. Jelinek-Mercer does not do this. It's the same kind of lambda for all documents. So enter other kind of a smoothing technique called the so-called Dirichlet smoothing technique, where your lambda is now actually dependent on the document length. So there's still a parameter, mu, but the actual, I mean, you can think of taking this particular expression, mu by document length plus mu, using this as lambda in the linear interpolation formula. And what that would give you is basically the Dirichlet formula. So I, again, kind of quick look at the earlier slides. I think, I mean, you've done things like good Turing estimation and kind of other advanced kinds of smoothing methods. I didn't kind of offhand see a mention of Dirichlet smoothing. Can you confirm whether that was already covered in detail or not? Anybody?
Linear interpolation is covered, sir.
But the Dirichlet part kind of, that wasn't covered, or kind of, is that correct?
Yes.
Can someone else please confirm?
No, sir, the second one wasn't covered.
Okay, so kind of, I am absolutely not going into the mathematics behind Dirichlet smoothing, but I'm kind of giving it to you from an intuitive point of view. And the intuition is, as I just said, if it's a long document, then probability of keyword T from the corresponding language model is more reliable, or I expect it to be more reliable than the same estimate taken from a short document. Therefore, what I want is, I want probability estimates from short documents to be smoothed to a greater extent. And kind of as the document length grows bigger and bigger, I want the amount of smoothing to be used to decrease. So that's the kind of intuition behind using kind of this form of lambda. Plug it in over here and you'd get the equivalent of a Dirichlet smooth language, kind of a term weight that uses Dirichlet smoothing instead of language linear interpolation. Okay, so so again, kind of I mean, it's always good to, I mean, again, kind of here, there is a definite intuition that suggests Dirichlet interpolation should, or Dirichlet smoothing should work better than linear interpolation. And this time, mercifully, experimental results confirm our hypothesis. And in practice, Dirichlet smoothing does turn out to work significantly better than linear interpolation or Jelinek-Mercer smoothing. So let's look at this. Okay, maybe kind of, if you've not already skipped ahead in the slides and looked at what's coming, think about the following question for a moment. Remember, my overall document scoring formula was, sorry, this. So assume for simplicity that, as with most of our user queries, every keyword occurs just once in the query. So then you can ignore the exponent. So it's basically a product of the probability of generating each keyword in your query from whatever document you're trying to score. So you can either think of it as a product of these probabilities, or equivalently, again, as Tanmoy sir has already discussed, for practical reasons, it makes more sense to talk about the sum of logarithms of these probabilities rather than the product. Very well. So let's come back to the formula that we've obtained so far using Jelinek-Mercer smoothing. So now suppose kind of focus on the Jelinek-Mercer smoothing formula and plug that in to the overall scoring formula for a particular document. So what I am essentially saying is I multiply these things together for different query keywords. Okay, now kind of take a quick look at it and notice that this T by kind of, this is, remember, this part is the maximum likelihood estimate. So this is corresponds to, I dip my hand into a particular document and pick out a ball of the desired color. So usual formula for this is number of occurrences of that particular term in the document divided by total number of terms in the document. So already if you start relating this back to the more heuristic kind of term weight that we had come up with earlier, which corresponds to kind of TF, some version of TF, IDF, and normalization, you can already see that this term, okay, so you tell me which ones of TF, IDF, and normalization do you see occurring in this particular term, the first term? So kind of, if you are confused, then this probability, remember, is number of occurrences of T. In other words, the TF of T divided by the total number of words in the document D. So kind of my question is, if you relate this to the conventional TF, IDF document length kind of term weighting, which one of those components do you see occurring in this term?
So TF,
Perfect. And
term frequency is there.
So
And
term
right.
frequency.
So you can clearly see that this is 1 minus lambda into TF divided by something. And what is that something?
the number of terms in the document.
So you can think of that as?
The number of words occurrence in the document.
Correct. So it kind of, if you have a downloaded copy of the slides of the earlier session, just kind of quickly flip back to those slides and see kind of what we could use the number of words in a document. I mean, what we could use that as an estimate of or in place of. So this slide itself contains a hint. Notice that that count I am kind of, this is the count that I have in mind.
Yes.
So this is essentially the
Number of
one form of the document length.
Yes, sir.
Yes, sir.
So basically what you have over here is kind of, even though we obtained this formula using kind of an entirely different model, what we end up getting kind of gives us some of those familiar ingredients. So in this particular term, 1 minus lambda into PT given theta d, you have the TF component, and in the denominator, you have some form of document length. But what's confusing is, okay, so then what is missing? I have TF, I have normalization. What am I missing?
We need document frequency.
Exactly. So, okay, now kind of let me extend that question a little. What we usually do is inverse document frequency. What that means is a term that occurs in many documents is likely to be, I mean, so basically kind of I'm revisiting the intuition behind IDF. A term that occurs in many documents is likely to be a general term, not very discriminatory. Therefore, I attach it less importance. Whereas something that is more specific occurs in a smaller number of documents, a match on such a specific term is probably more important. Therefore, something with a low document frequency, I attach a higher importance to. So kind of that's basically the intuition behind why I use an inverse document frequency factor. Common terms are not important. Specific terms, less common terms, those are more important. Do you seek any contradiction or at least any apparent contradiction in the formula that I have under linear interpolation? So look at the second term. This one we've already kind of...
So here, because of the second term, the terms which occur more number of times will get more importance, like over here.
Excellent. Thank you. Thank you. That's exactly the kind of the apparent source of kind of confusion that I wanted at least one of you to point out. So if you look at the second term here, what it seems to suggest is, this is kind of, remember PT given C, the way I was estimating this was total number of occurrences of that term in the collection divided by total number of terms in the collection as a whole. So if a term is commonly occurring, this expression will be high. If a term is kind of rare, then this expression will be small for a rare term. So kind of that doesn't fit in very well with kind of our earlier argument. Kind of earlier argument was TF, your term should increase. Fine, that much we have over here. TF over here high means this quantity will increase. Document length more means your term width should decrease because you're dividing by the document length. That part also agrees over here. But kind of the heuristic method, we were saying rarer terms are better, and this on the surface appears to be contradicting that. Now it turns out that because we have these two things multiplied together as 1 minus lambda and lambda, in spite of what this appears to do, the actual effect is indeed what we want it to be. So kind of let's do a little more arithmetic manipulation and then it will become clear to you why that is the case. I'm sorry, this is again taking me back to the beginning of time. Sorry, there's something wrong with my keyboard. Right. So kind of this is basically what I was talking about. This was our original formula. Assuming that I just have kind of, okay, I mean, for simplicity, assume that you have distinct query words. So it's simply the product of probability of obtaining a particular query keyword from the document that I'm trying to score. And this is the smooth probability of obtaining this term QJ from the document D, where I've been using linear interpolation or Jelinek-Mercer smoothing. And kind of, as one of you pointed out, and as I wanted, apparently a high collection frequency seems to be giving you a high weight. And that's not what we want. So now do a little more arithmetic manipulation. So what I do is I divide throughout by this particular term. So it's 1 minus lambda into something plus the collection frequency term. So I divide this entire expression by the collection frequency term. So now what I have is this becomes 1 plus this term divided by the collection frequency term. So basically I now have 1 minus lambda by lambda into this term remains as it is, but because I've divided by this term, I now have collection size in the numerator and collection frequency in the denominator. What have I kind of quietly left out? Remember that this was basically kind of, think of this as capital X plus capital Y. And I wrote that as capital X plus capital Y divided by capital Y. So capital X plus capital Y divided by capital Y gives you 1 for the Y term, and capital X by capital Y gives you this term. But kind of why did I quietly divide by y and not adjust for it elsewhere? So here's the explanation for that. What have you actually done? You've basically done this for every query keyword. So to kind of correct for this, just because I've divided this term by this quantity, to restore the balance, what I should do is I should multiply by this quantity also. Everybody with me so far?
Yes, sir. Yes, sir.
So kind of the factor that I've kind of quietly eliminated is basically this product or kind of this quantity for each query term, and then I multiply it over all query terms. So think about that component, that is the multiplicatory factor that I've kind of quietly left out over here. That is basically the product of this term over all query terms. It's free of any document component. So the product of, suppose, I mean, think of a simpler Q1, Q2, Q3 query, then this expression for Q1 times this expression for Q2 times this expression for Q3, that value is going to be the same for every document, because I'm just looking at the collection frequency of the query terms, not the document frequency.
Yes, sir.
So now if I kind of, what was I really interested in? I was really interested in computing a score for each document and then ordering the documents by that score. So if instead of the original scores, I kind of cancel out a common factor from all the original scores, as long as that's a positive number, I still get the same ordering. So basically what I've done is I've taken again kind of this factor for each query term, multiplied it together over all query terms and gotten a number that is independent of any document. Now, if I divide all document similarities by that particular fixed number, I'll get my updated document similarities. But that updated document similarity will give me the same ranking or the same ordering as my original formula. So kind of basically the point to make is that don't be fooled by the fact that there is a plus CF by C over here, because it's 1 minus lambda times this plus lambda times this, and then this is being multiplied by everything else. This actually kind of a high collection frequency actually does not end up promoting a term. Rather, a term that has a high collection frequency actually gets or contributes less towards the overall score of a document compared to a more specific rarer term. So kind of if you go from here to here, one transformation is straightforward. That's just the kind of product of probabilities to sum of their logarithms. That part is kind of standard. But what the other thing that I've done, hopefully you are now convinced that the factor that I kind of quietly erased over here is the same for all documents. And because it's a positive number, it's something that will not affect document ordering. So kind of even though kind of less final conclusion is that even though I obtained a ranking function using a very different kind of model, what we eventually arrive at is once again a combination of the DF factor and IDF factor and document length normalization. Okay, so maybe kind of one relatively kind of minor angle to this, minor angle because we'll see that it's kind of mostly of theoretical rather than of practical importance. So if you now kind of think back to what our kind of this smoothing factor, what did our smoothing factor actually do? Two things. One of the reasons why we introduce smoothing is to get rid of the zero probability problem. So via smoothing, you hope that you have more reliable probability estimates. The other thing is that what we find is that in spite of the apparent occurrence of CF in the numerator here, what's really happening, the way this arithmetic is working, is that you are actually getting the IDF effect from this term. Or in other words, smoothing is also giving you the IDF effect. So kind of two effects. Smoothing is one, it's helping you to avoid the zero probability problem. Remember that that is with regard to kind of when TF is equal to 0, you don't automatically kind of give the document a score of 0. So that is one effect of smoothing. The other effect of smoothing that was not clear, but which kind of we obtained via all this arithmetic manipulation, is that smoothing actually brings in the IDF effect into your term weights. So now kind of let's look at one other detail that I've kind of quietly skipped over in all these discussions. First, when we were just looking at linear interpolation versus Dirichlet smoothing, there the idea was linear interpolation uses the same kind of smoothing for all documents irrespective of their length. Whereas Dirichlet smoothing kind of adjusts the amount of smoothing kind of by taking length into account. So a short document, estimates are smoothed to a greater extent. A long document, you use less smoothing. So kind of what I remarked in passing was that the Dirichlet smoothing method seems to be a better idea. And in fact, experimental confirmation has been obtained for that expectation that kind of Dirichlet smoothing does in fact work a good deal better in practice. But the other, this claim that smoothing brings into effect or brings the IDF factor into effect, that part I only used the Jelinek-Mercer or the linear interpolation formula. So kind of one argument might be, should we do kind of both kinds of smoothing? Jelinek-Mercer smoothing for the IDF effect, and then Dirichlet smoothing for improving the estimated probabilities. And kind of, so that also people have tried based on this idea, and it's called kind of two-stage smoothing. And it's exactly what I said. You use Dirichlet smoothing to address the small sample problem, and you use linear interpolation to distinguish between good matches, that means a match on a very specific rare query term, and a match on a kind of more general query term. So both of these have been put together in a formula that looks like this. So this is the kind of the two-stage, and you can see that this part is where Dirichlet is playing a role, but you still have a 1 minus lambda plus lambda form, and this is the collection frequency, and this via the arithmetic manipulation we discussed earlier is going to bring the IDF effect into picture. Downside is that earlier we had only one parameter to worry about. Now you have to kind of, in a practical system that you want to use for searching, you now have to come up with appropriate values for lambda and mu. And once again, even though this kind of seems like a nice idea, experimental results kind of suggest that it's not worth doing something this complicated. So kind of the quick summary is that two-stage smoothing, even though it sounds like a good idea, is kind of in practice, it turns out not to work that much better than a single-stage Dirichlet smoothing. So kind of final take-home summary is that if you are using a language modeling based term weighting scheme, just stick with an appropriate choice of a Dirichlet smoothing parameter and you will be fine. Okay, I think we'll stop with the language modeling discussion here. Again, take another very quick break. It says 41 now, so we'll get started by 45. Meanwhile, if there are any questions related to this part, then we could discuss that. Otherwise, I mean, the rest of you can take a quick breather, and we'll start again at 16:45. Sorry, somebody had a question?
Yes, sir.
Yes.
Actually, experimentally, you said that the two-stage smoothing is not performing really great. Is it because of more number of parameters to worry and optimize? Because the idea does seem good. I didn't understand that.
Oh, well, I mean, see, experimental results are, no, it's not the case that kind of, because parameter tuning is harder. So I kind of don't recall 100% of kind of the paper, but my recollection is that parameter tuning was kind of done retrospectively, so to speak. So you try the entire, all possible combinations of parameters. So it's not that it's just harder to get good parameter values, but even with tuning, it turns out that kind of, even though you expect a benefit, that in practice, that benefit doesn't kind of happen too often. So kind of it's something that kind of you observe all the time when you're dealing with real data sets. I mean, you have a wonderful mathematical model, kind of suggests that it should work really well, but your data doesn't kind of fulfill your expectations. So that happens all the time.
Okay, sir.
So I don't have a very good explanation for why that happens, except to say that language is like that, people are like that, documents are like that. Just that. I mean, that's the lame explanation I can offer.
Okay, sir. Thank you, sir.
Okay, the next thing we'll start in a couple of minutes is kind of ways to quantify this business of kind of experimental results being good, bad, what do they mean, and what do typical data sets look like. That's the discussion that we'll have next. Okay, so before we get started with the discussion on how to tell whether a retrieval system is doing well or not, just a quick question. If you do not know what recall, precision, and F1 are, can you please raise your hand? Or just kind of send a chat in the chat window, unmute your mic, whatever. Right. So what I'll do is I'll kind of, the preliminary is mostly introduce notions of recall and precision. Okay, on second thoughts, maybe I will kind of just quickly go through the slides in the preliminary section, basically because they introduce a term that you may or may not kind of encounter if you do more reading on the subject. So it's really again kind of a fancy name for kind of a fairly straightforward notion. So it's basically the name given to a standard protocol used for determining how well retrieval systems are performing. So this fancy term it's called the Cranfield paradigm or the Cranfield method. What it really means is kind of, it's nothing more complicated than if you want to evaluate a retrieval system or a search engine, what you need to do is kind of, evaluate it. Basically, remember that evaluation is always with an eye to a comparative evaluation. So given two algorithms, you want to decide which one to use in practice. So what we really need the evaluation for is to kind of compare two or more different algorithms. So as you would expect, the obvious way to do this is give the same document collection to all the systems that you want to compare, give or submit the same user queries, and if you have the ground truth or the gold standard data for these particular queries, specifically what we need is which document is relevant to which query. So that's the information that you need. If you kind of use this kind of a data set to compare all algorithms, you're doing a fair job. So this fairly obvious method of evaluating and comparing search engines is called the Cranfield paradigm, and kind of dates from well before I was born, so kind of from sometime in the 60s. And kind of, again, kind of just to repeat the point that it's a very familiar kind of evaluation framework. You can think of the document collection as a kind of syllabus. Query, a set of queries is basically your question paper. And the relevance judgments, what I was loosely describing as the ground truth or kind of gold standard data earlier, is basically information about which document is relevant to which query. So I think the only reason why it's a good idea to explicitly mention or discuss this evaluation framework is that it also gives us an opportunity to kind of formally recognize what the limitations of this Cranfield method are. And can you look at the assumptions behind computing recall and precision for different systems using this kind of benchmark data, and you think for a moment, these assumptions should kind of come across to you as shortcomings. So we look at them one by one. So first is, given a particular query, you, I, and all of us would agree on which document is useful and which document is not. And kind of you know from your experience that that's not the case. There are any number of queries being submitted by any number of people I mean, same query being submitted by any number of people worldwide to a particular search engine. And it's not the case that everybody finds the same tutorial or the same PDF file or the same video equally useful. So that's one. Secondly, what we need is kind of this ground truth, even though I haven't talked about it explicitly. What the ground truth should tell us is kind of exhaustive information about which document is relevant to which query. So kind of what do I really mean there? I mean, it's sort of like you have a history question that asks like, what were the causes of the Sepoy Mutiny in 1857? And maybe your textbook gives, say, 6 reasons. In order to get full marks, you have to include all 6 reasons in your answer. So kind of just relate that to the terms that you've been talking about so far. So that's basically, I'm talking about recall. So unless you get 100% recall, you don't get a perfect score. Now, in order to compute recall, I need to know kind of the exhaustive set of all useful documents for a particular given query. So that's basically what I've kind of explicitly stated in the second assumption, that in order to use this Cranfield method, in order to do recall precision-based evaluation, I have to know for a particular query the set of all relevant documents in the collection for that query. Third, kind of, it's like, kind of again, revisit the example that I just mentioned. 6 causes of the, say, 6 causes of the Sepoy Mutiny of 1857. Maybe not all of them are equally important. So if you forget about one of the more minor contributors, maybe your teacher doesn't penalize you too much. Whereas that kind of thing in the usual recall and precision computations, we don't do. So kind of any relevant document is as good as any other relevant document. So basically, it's just kind of any relevant document is like a 1, and any non-relevant document is 0. So again, that's kind of counterintuitive. We know from our experience that there are more useful documents and less useful documents. Okay, now what we will do a little later, while we are kind of discussing the details of how evaluation is done, is that the 3 assumptions that I've mentioned so far, we will talk about them in a little more detail, and we'll see kind of workarounds, or kind of at least figuring out to what extent the relevance of a document to a query is objectively discernible. Do you really need to know all relevant documents in the collection? What if you want to kind of introduce the notion of very useful, partly useful, not so useful? So what I'm trying to say is the first 3 assumptions we will revisit and try to find ways to improve our evaluation method so that kind of these assumptions don't have such a strong impact anymore. But the 4th assumption, that the relevance of a document is independent of the relevance of other documents, kind of this is a very hard nut to crack. So kind of what do I really mean when I say relevance of a document is independent of the relevance of other documents? So suppose you want to know kind of what was Australia's score at stumps today. So there are a number of kind of news-related sites, sports-related sites that will give you the same information. So you kind of search for this and you get a kind of 10 links. You look at the first one, maybe you look at the second one for confirmation. But that's it, right? I mean, kind of, even though the 3rd, 4th, 5th, 6th, 7th, and so on, I mean, all of them may contain the same information. they're not useful to you because they're not providing you with any new information. Whereas when it comes to scoring a system, recall and precision-based scoring would mean that kind of I need to know, I mean, whether the fourth document is useful or not. I cannot make that dependent on which documents I have seen at ranks 1, 2, and 3. So this kind of turns out to be, I mean, I don't know of any reliable way that has been proposed to kind of take the reading order of a user into account when kind of evaluating systems. So kind of the fourth assumption is something that we will have to accept kind of as a possible weakness. That so I mean, if after 3 documents you see another copy of the same document that contains the same information without providing you any new information, you still have to regard that as useful. But the other first 3 assumptions that I just discussed, we'll look at ways to kind of weaken those assumptions or kind of do without them. Okay, so since kind of you're all familiar with the notions of recall, precision, and F1, kind of let me jump straight to slightly different metrics. So which are basically motivated by the fact that recall and precision, and therefore F1 as well, they are all set-based measures. So if I look at these 2 ranked lists, both contain 5 documents. More specifically, both contain 2 useful out of a total of 5 documents retrieved. So if you compute recall and precision, both these sets are going to look identical. Whereas kind of, what does your intuition tell you? I mean, is there one that you would prefer over the other? Anyone? I mean, I give you 2 of these lists in response to one of your queries. You find that one of the lists has 3 not useful, followed by 2 useful, and the other has 2 useful, followed by 3 not useful. Which one would you prefer?
The second one, sir.
The second.
Correct. So that's what I think most of us would agree. But kind of precision wise, what's the precision value for the 2 lists? Anybody? So precision, remember, is number relevant retrieved divided by the number retrieved. So I have 2 useful out of 5 retrieved. So my precision would be
2 by 5.
0.4 in both cases. So
0.4.
right. So recall, precision, and F1 kind of don't distinguish between these 2 rankings as I want them to. So that brings us to a metric called average precision. And again, kind of if you're looking at papers dealing with retrieval techniques rather than kind of more sophisticated NLP tasks, you probably see kind of references to average precision all the time. So let's look at what average precision is. And then kind of I'll tell you later why average precision, I mean, the version that we're talking about, why it's called non-interpolated. So the idea is the following. So I'll kind of just walk through this example to tell you how non-interpolated average precision is computed. So I'll assume that I've changed the example a little. So now I have 6 retrieved documents, documents at ranks 1, 3, and 6 are useful. The others are not useful. And remember the assumption behind recall computation. I somehow know, because of the nature of my ground truth data, that for this particular query, there are a total of 5 relevant documents. So what I do in order to compute non-interpolated average precision is the following. I start going down the ranked list of documents one by one. Every time I encounter a relevant document, my recall goes up a little. So if I have capital N number of relevant documents, every time I encounter a relevant document, how does my recall what does my recall increase by?
Relevant document.
Correct. So my question is the following. So suppose I have capital N relevant documents in my collection. My ground truth has already told me that. Now what I am doing is I am looking at my ranked list, and because of the ground truth, I also know which is relevant, which is not relevant. So corresponding to each rank, I write down the recall value and the precision value. So first time, for this particular example, I find a relevant document. So now I have, remember, the assumption is that I have 5 relevant documents in all. So my ground truth has already told me that. So right now I have 1 out of 5. My recall is 0.2. My precision is retrieved 1 so far, and it was good. So my precision is 1. Second turns out to be a non-relevant document. So my recall does not change. I ignore it. Third document is again a relevant document. So my question is, if in general there are capital N relevant documents for a particular query, then when I'm going down a ranked list like this, every time I encounter a relevant document, what will my recall increase by?
So 1 by N.
Perfect. So here it goes up to 0.4. Again, no change in recall. Sixth document, my recall is 0.6. And that's where assume that that's where my search engine has terminated its results. So I don't have anything anymore. So corresponding to each of these recall points, I compute what the precision is. As we said, like here it's 1 out of 1, here it's 2 out of 3, and here it's 3 out of 6. What about recall 0.8 and 1.0? I never achieved those. So what I assume is that in the worst case, those documents would be like ranked at infinity. So I extend my ranked list and fill in these worst case scenarios. So the remaining 2 relevant documents, I assume they are ranked at infinity. So by the time my recall gets to 0.8 or 1, my precision has dropped to 0. And now what I compute as the average precision is average of the precision values over all these recall points. So this is what my average precision looks like. I have 5 recall points. So 3 non-zero precision values and 2 zero precision values. So the average is 1 by 5 of 1 plus 0.67 plus 0.5. So basically, because I am taking the average of precision values over all the recall points for that particular query, this is called average precision. But don't be fooled by its name. Even though it says average precision, and even though it is you're computing an average of precision values, because you are computing the average over all possible recall points. This is a combined measure that takes both recall and precision into account. So we'll see a little bit more about that in a moment. Plus, it is something that takes ranking into account as well. So maybe let me get the easier possible source of confusion out of the way first. Even though it says average precision, I'm claiming that it does somehow also reflect recall, in the sense that if you have two systems and one retrieves more relevant documents than the other, but for the documents that they retrieve in common, the ranks are the same, my claim is the document that retrieves more relevant documents will get a higher average precision. Does everybody see why that is the case?
Yes, sir.
Yes, sir.
Great. So even though I've called it average precision, it's actually affected by recall as well. So the more relevant documents you retrieve, the more non-zero scores you will have, and therefore the higher your average precision. Second question, or kind of second issue that we were interested in, is kind of, this is what we started with, and in terms of just recall or just precision, both of them would get the same score. So the reason behind computing average precision was that kind of it was supposed to capture or take into account better ranking. So kind of for simplicity, what you can assume is that kind of suppose this sixth document, which was relevant over here, for a different system, it moves up the ranks a little bit. Then what will happen? Whatever its new position is, 0.6 recall will be the same, but its precision will improve.
Precision will increase.
Exactly. So kind of that's the argument behind why kind of average precision is actually affected by ranking. So kind of average precision seems to be a nice thing in that it's affected by recall, it's affected by precision. So in that sense, it's kind of like F1. But the advantage over F1 is that it's also affected by ranking. So kind of usually when you're talking about rank results, you prefer average precision to F1. Let's see. So maybe as a kind of quick exercise, kind of if you're not convinced by this argument, then maybe you could kind of quickly work this. I mean, assume a certain number of relevant documents for the particular query that we're discussing here, some 5 or 10 or whatever makes your life easy, and work out the non-interpolated average precision for the two lists, and that should kind of give you a definitely higher number for the list on the right-hand side. So which is basically the effect that we wanted to achieve. Okay, so now I think the remaining question is kind of, this is how I calculate average precision. Why am I calling it non-interpolated average precision? I mean, that suggests that there is an interpolated version of average precision. So what does that really mean? So before going into interpolated average precision, so think back to the fancy Cranfield paradigm that I talked about. And remember that just like any exam question paper that you have been given, the Cranfield paradigm also in order to test a particular system, it will also not depend on the outcome of just a single query. So you'll have a collection of kind of, usually 50 is regarded as a good number. 50, 100, the more questions you have, the more reliable your evaluation. So basically, you're going to do your average precision calculation over a set of 50 queries. So, and kind of one point to note is that your average precision for any individual query is guaranteed to be between 0 and 1. So the number of possible values here are equal to n. The highest possible precision value that you can have ever is 1. So in the best case, your sum over here would be equal to n, and then you divide by n. So in the best case, your precision would be, average precision would be 1. So that's the maximum value. The minimum value is 0 if you don't retrieve any useful documents at all. I just kind of, again, take 2 seconds to reflect on what the ideal retrieval scenario is. So when kind of, what would your rank list look like in order for you to get an average precision of 1? So suppose you have kind of, again, for a particular query, suppose you have 10 relevant documents. In order to get an average precision of 1 for that particular query, what would your system have to do with those 10 documents?
That all the 10 should be relevant.
All the first 10 should be relevant, or in other words, kind of the way I put the question is that if you have 10 relevant documents for a question, in order to get an average precision of 1, your system has to rank them at ranks 1 through 10. So basically all the relevant documents first, followed by all the non-relevant documents.
Non-relevant.
If you do that, then you get, I mean, if you can do that for a particular query, that's the best you can do. I mean, given all our assumptions about all documents being kind of, I mean, any relevant document being as useful as another. So kind of, given that we don't distinguish between 2 relevant documents and regard them as equally useful, in order for a system to get a perfect score, average precision 1 for a particular query, it would have to retrieve all the relevant documents and rank them at the top of the rank list. Okay, coming back to why am I calling this non-interpolated, and then there must be an interpolated version. So what is the interpolated version? So main thing is kind of 2 points. One is that in order for your evaluation to be reliable, of course, you don't depend on a single query. So you'll have a set of 50, 100, however many queries. So you'll need kind of an average score across all these queries to get an overall indication of how well your system does. And kind of that's usually referred to as the mean average precision, or MAP. MAP for short. Mean average precision means remember mean average precision, the average is over recall points for a particular query, and the mean is over the set of all queries in your test collection. Okay, clear? What's the difference between the mean and the average? So now let's look at why I might need interpolation. So for that, here's my question. So kind of you work this out and you get a certain number. And I tell you that for a particular set of 50 test queries, your system has achieved an average precision, a mean average precision of 0.4. Minimum could have been 0, maximum could be 1. So in some sense, you could also say that your mean average precision, your system's mean average precision score for this particular set of test queries is 40%. Now, is there some kind of easy human interpretation for that 40% figure? notice because of the complicated way in which we are calculating average precision, it's not something like you can say, okay, for 40% of the time it gets the answer right. Or that's not the case, right? I mean, it's kind of affected by ranking. What's happening is you're taking an average across recall points. So kind of just saying that mean average precision is 0.4 or 40%, kind of there's no easy human interpretation for that particular score. So basically that's what leads to the formulation of the interpolated average precision. So here's the idea. Again, kind of the two things that I mentioned. One is kind of, suppose you have kind of, instead of 50 queries, let's just look at 2 queries, Q1 and Q2. And as kind of one of you correctly answered, if Q1 has 3 relevant documents, the recall points for Q1 will correspond to 1/3, 2/3, and 1. Q2 has, suppose it has 4 relevant documents, then the recall points will be 1/4, 2/4, that's half, 3/4, and then again 1. So if different queries have different numbers of relevant documents, and kind of that's only to be expected, then you look at these different lines for the different queries, kind of the X, kind of, I mean, where you have actual points on the curve, they will be different for different queries. So now consider the following. Instead of having kind of like Q1 has 1/3, 2/3, 1, Q2 has 1/4, half, 3/4, 1. So could we somehow, using interpolation, standardize a set of recall points on the x-axis? So say something like, for all queries, I compute recall at, I compute precision when recall is 10%, 20%, 30%, and so on. So then, I mean, first notice that if my query has only 3 relevant documents, there is no way I can ever achieve 10% recall. My kind of unit of retrieval is a single document. So my kind of recall jumps up by 1/3 every time. So there's no way I can get 1/10, 2/10, 3/10, and so forth. Likewise for anything that has 4 relevant documents. So kind of if I want to standardize the recall points over here as 10%, 20%, all the way up to 1%, 100%, then I will have to do some kind of interpolation. So that's basically kind of what leads to interpolated average precision. And now, kind of what does that have to do with the other question that I raised earlier? I mean, does it give you something that is interpretable? In a sense, yes. So if I give you, suppose I have somehow via interpolation, and the precise mechanism of interpolation will come to a little later, but suppose via some interpolation method, for every query, no matter how many relevant documents it has, I am somehow able to compute an interpolated precision value at 10%, 20%, 30%, all the way up to 100%. Once I calculate these values, now I can calculate a mean interpolated average precision value at 50% recall. So basically what I'm saying is I've kind of used some interpolation to smooth all these lines. And now I'm kind of every line I'm looking at the 10% point, the 20% point, and so on. So kind of every line now has an interpolated point at 50%. So I calculate the average or the mean across all these points, and I get a certain particular value. So in contrast to the mean average precision, what I have calculated now is the mean interpolated average precision at say 50% recall. And now suppose I tell you that this number is 0.4. The advantage over here is that kind of the fact that my system has achieved a mean interpolated average precision of 0.4 at 50% recall. What that basically means is, on average, by the time my system has retrieved half the relevant documents for a particular query, I can expect about 40% precision. So you give me any query, by the time I get about half the relevant documents, I should expect to get 2 out of 5 useful documents. So the kind of interpolation has permitted me to use the same recall points for all queries, and therefore to compute an average at each of these standardized recall points, and then the average or the mean computed at each of these standardized recall points has a certain interpretation. So that's the precision that my system achieves on average when its recall is, say, 0.5 or 0.2 or 0.3 or whatever. So that's basically the whole idea behind why we sometimes want to calculate an interpolated average precision. I can't kind of see you, so I can't tell whether this made any sense. Can you tell me whether this made any sense at all? I mean, why instead of instead of non-interpolated average precision, why I might want to do some kind of interpolation? I mean, should I take that as a no, it doesn't make sense at all, or what?
No idea, sir.
Okay. Okay, so I mean, it's not terribly important, so kind of I'll take another crack at it. If it still doesn't make sense, then we'll kind of skip it. So here's the idea. First, are you in agreement that we can't rely on a single query?
Yes.
Yes, sir.
Yes, sir.
Okay, so now the problem with different queries is that in general, they will have different numbers of relevant documents. What does that have to do? I mean, say basically what that means is, if you look at the example I have over here, for Q1, my ground truth tells me that there are 3 relevant documents. Q2, my ground truth tells me there are 4 relevant documents. So that means my ranked list for Q1, when the first relevant document is retrieved, my recall shoots up directly from 0 to 1/3, then to 2/3, and then finally to 1. Likewise, for my Q2, the 4 relevant documents that I have, assuming that I've managed to retrieve all of them at certain ranks, first relevant document, my recall is 1/4, half, 3/4, and then finally 1. So what I am trying to do is, because different queries have different numbers of relevant documents, and kind of for a particular query, your recall points, remember, goes up in the form kind of 1 by capital N, then 2 by capital N, 3 by capital N, all the way up to 1.0. And because this capital N is different for different queries, these will correspond to different points on the x-axis. What I want to do is, instead of these kind of different points for different queries, what I want to do is somehow, via interpolation, compute interpolated precision values at, say, 10% for all queries. So what is the real average, real precision at 10% I may not achieve. So for Q1, my recall never actually is 10%. Q2 recall is never actually 10%. So I'll have to use some kind of estimation or interpolation in order to calculate a supposed precision that the system would achieve for Q1 at this hypothetical 10% recall point. So that's kind of, I haven't said what or how I am going to do the interpolation. All I'm saying is, why is interpolation necessary? And that's basically because if I can standardize some recall points here, then I can kind of make the following observation. So say 50% recall is a standard point. Now 50% recall kind of for question 2, because it has an even number of relevant documents, there is some position in the ranked scale, so in the ranked list where 50% recall is actually achieved. But if a query has an odd number of relevant documents, nowhere in the ranked list will you have obtained exactly half the relevant documents.
No, sir.
Clear?
Yes, sir.
Okay, so that's exactly what this kind of picture is trying to suggest, that for this particular query, query 2, 50% is actually a point on the curve. But query 1, 50% and kind of x-axis 50% does not correspond to a real point on the curve. So what I'm saying is, given that I have an actual point on the graph at 1/3 and another actual point at 2/3, I am going to use these values somehow to compute an interpolated value at 50%. So again, I haven't said how I'm going to do the interpolation, but if I have some method of interpolation, then I can use that to compute a precision value for all queries, no matter how many relevant documents they have. I can compute a precision value at 50% recall. So once I've done this, either directly or via interpolation, once I have a precision value for every query at 50% recall, I can compute the mean of all these values and get a certain number. Again, that number will be between 0 and 1. So suppose that number is 0.4. Is that more interpretable than a non-interpolated average precision value of 0.4? My claim is yes, it's more interpretable now. What I can say is, for the average query, when this particular system retrieves half the relevant documents, that means by the time it has achieved 50% recall, it will have a precision of 0.4. That means for any given query, what I expect is by the time it retrieves half the relevant documents for that particular query, I will get 2 out of 5 useful documents. So basically what interpolation has permitted me to do is, instead of different points on the x-axis for different queries, I use interpolation to fix a set of points on the x-axis. And for each such fixed point on the x-axis, I get a certain average precision value, specifically an interpolated average precision value for all the queries in my collection. And then when I have compute the mean across all these values for all the different queries, I get a mean interpolated average precision at, say, recall equal to 10%, recall equal to 20%, and so on. And the interpretation is, as I said, that on average, when your system achieves 20% recall for a particular query, on average, it will have a precision of about, say, 0.4 in the example that we were using. Okay. Well, I'm sorry if that didn't make too much sense, but kind of, I think the recordings will be available so you can
Yes, sir, we
go over
got
this
it.
period again. And maybe you can send me email if it still doesn't make sense. But because it's not a terribly important metric, I think I'll move on to the other metric that you are kind of two others, I think, that you will see quite frequently if you read papers on IR. So basically, you notice that kind of the actual interpolation mechanism that I'm skipping over because that will again take a little time to explain. And kind of I spend more time on this than I should have. So I'll skip over to the two other metrics that you'll see commonly used. One is very easy to interpret. That's kind of precision at rank K. So this is basically for each query, you compute the precision after K documents have been retrieved. And then, as always, you compute the mean across all your 50 queries or 100 queries or whatever. So the advantage of this, in contrast to mean average precision, remember by that I mean mean non-interpolated average precision. In contrast to that, the advantage is this has a very simple, easy interpretation, in the sense that if I tell you that your P at 10 is 0.6, what I'm saying is, on average, for the 50 or 100 queries in your test collection, if you look at the top 10 documents retrieved by your system, on average, 6 of them have been found to be useful. So advantage of precision at K is it has a very easy interpretation, but it turns out not to have kind of certain statistical properties. Again, I won't go into those. So by all means, kind of look at precision at 10, precision at 20 values, because they're telling you what's happening in the top ranks, say the top 10 documents or top 20 documents retrieved by your system. But don't rely exclusively on them in order to compare two different retrieval algorithms. Last evaluation measure that I want to talk about, again, something that you might encounter in the literature, is something called, kind of, we're eventually going to build to something called NDCG, that's short for normalized discounted cumulated gain. So kind of what we'll do is we'll add one letter to the acronym in one step. So we'll start with the notion of gain, then cumulated gain, then discounted cumulated gain, and then finally normalized discounted cumulated gain. Okay, so what's the fundamental new thing that we are trying to achieve by moving from mean average precision to cumulated gain? The basic difference is that, remember the assumptions that I discussed earlier? Over there, I said that every relevant document is considered to be equally useful. So you get a 1 for a relevant document. Indeed, you get 1 for any relevant document at all, and you get a 0 for any non-relevant document. But as humans, we usually want to make more fine-grained distinctions. So in particular, we want to make a distinction between highly relevant documents or very useful documents and kind of okay-ish documents that are useful but not that useful. So instead of kind of 0 for a non-relevant document and 1 for a relevant document, we introduce the notion of a gain. So basically, sorry, again, I'm back where I was. Right. So for example, I could define 4 levels of gain. So a document with gain 0 does not give me any benefit at all, so it's non-relevant. A document with a gain value of 3 is very useful. So that's the kind of document that I would want to retrieve. And gain 2 is useful. Gain 1 is kind of marginal. I mean, it may be some little bit of useful information, but not that useful. So basically now what I am permitting is the people who create the ground truth data, earlier they had to kind of, for a particular query, they would have to look at a document and they were permitted only to say, yes, this document is useful, or no, this document is not useful. So now what I have allowed them to do is look at the query, look at a document, and give the document a score between 0, 1, 2, and 3. So now the person or the persons who give the human judgment, the persons who make up the or create the ground truth data that we are going to use later for evaluation, they can now make more fine-grained distinctions between queries. Between documents for a particular query. Okay, so suppose that I have a kind of test collection, and as I said, for this particular test collection, my ground truth data does not simply say relevant, not relevant. It says, the humans who created this ground truth data tell me that for a particular query, this was gain value 3, this document had gain value 2, and so on. So now I run my system for a particular query, get back a ranked list, and then I look at my ground truth and find out what was the value of the particular, what was the gain value of the particular document that I retrieved. So what this list I'm going to refer to it as the gain vector. What this gain vector means is basically the document at first rank had a gain value of 3. The document at second rank had a gain value 2. Then the third rank document again was very useful, so it had a gain value of 3. The fourth and fifth documents retrieved turned out to be not useful at all, so their gain values were 0, and so forth. So basically, I take my ranked list of documents returned by my search engine. For each document returned by the search engine, I look up the ground truth. My ground truth is telling me that this has a gain value of 0, 1, 2, or 3, and I put that number here, and that's basically what gives me the gain vector. Okay, is everybody with me so far on how the gain vector is created?
Yes, sir.
Okay, so this, remember, this gain vector is giving me the gain values at kind of different ranks, for the different documents at different ranks. So now if I want to look at how well I've done up to rank 5, what I do is I compute now. So that was my C. Now, that was my G. Now I'm introducing the C into the acronym. My cumulated gain at rank I is simply add up all the gain values of all documents that you have retrieved so far. So cumulated gain at rank 1 is 3. Cumulated gain at rank 2 is 5. Cumulated gain at rank 3 is 8, and so forth. And in fact, you can see that cumulated gain up to rank 5 remains 8. Okay, so that's kind of cumulated gain. But again, you can see that cumulated gain by itself is not a very good idea, because 3, 2, 3, 0, 0 and 0, 0, 2, 3, 3, these two gain vectors. So again, think of what I'm talking about, the one that you see on the screen, and another gain vector that goes 0, 0, 2, 3, 3. So both of them will have the same cumulated gain at rank 5?
Yes, sir.
Okay. But again, kind of your intuition tells you that anything, this is better, right? I have 0, 0 at the end, whereas the other one was 0, 0, 2, 3, 3. So I have to adjust these gain values with regard to rank. So that's basically where discounting comes in. So every document has kind of whatever the human judge said was its kind of gain value. That is basically, I regard that as the standalone or intrinsic gain value. Once I put that document in a ranked list, the actual or discounted gain that it gets is kind of dependent on where it appears in the ranked list. So kind of The discounted gain, just look at this expression here, GI by some kind of damping factor. So again, the exact arithmetic formulation of this is what is commonly used, but it's not the only possibility. So what you are essentially doing is that a document has a standalone gain value of GI, but if it is ranked at rank I instead of rank 1, then its effective gain will be lower because it's kind of retrieved below. So I divide by some increasing function of I. And now when I calculate discounted cumulated gain, instead of kind of adding up just the gain values without any discounting, I now add up the discounted gain values. So kind of if you go to the previous example, this one will probably have its full gain. These 2 will be downgraded a little because it is at rank 2. 3 will be downgraded even more because it is at rank 3 and so forth. So now for kind of basically I've now also incorporated the notion that 2 things now I've done. One is new thing that I've been able to introduce is that documents can be very useful, quite useful, not so useful, like that. I mean, different grades of relevance. Plus, I have again reintroduced the thing that we wanted to achieve via mean average precision and taken ranking into the picture. So any document has a standalone gain, but its effective gain, what I'm calling its discounted gain, is actually calculated based on what position it appears in the rank list. And then I just add up. I mean, if you want BCG at rank 5, I add up all the discounted gain values of the documents ranked 1 through 5. Okay, now so far we were just talking about one single query. You'll kind of, as we've been saying repeatedly, for a reliable evaluation, you need a set of 50 or more queries. So how do I do this averaging across queries? Now the problem is different queries will have different numbers of documents with kind of 0, 1, 2, and 3 gain values. So a document that has a query that has many high quality documents will have plenty of relevant documents with gain value 3. Whereas another harder query, maybe it has a smaller number of documents and maybe their gain values are also lower. So averaging across documents like, averaging across queries like this doesn't seem to be a good thing to do. So what we are going to do finally is do this. Sorry, I have no idea where these lines appeared from. Just ignore them. The last thing that I'm going to do is introduce the final N into my acronym. So I'll have a normalized discounted cumulative gain. And the way I'm going to do that is for any particular query, I look at my ground truth gain values, and then I ask myself, what would the best possible retrieval result for this particular query look like? So let's again go back to the previous example. So say this is the gain vector corresponding to a particular ranking. You tell me what would you regard as the best possible achievable by a system? So in terms of the document ranking and the gain values that I have over here, what would you regard as the kind of ideal retrieval result? Can somebody please volunteer?
All threes
No, sir.
followed by all
Perfect,
twos.
perfect, perfect. So it's really a straightforward idea. So all threes followed by all twos, followed by all ones, and then all the zeros. So that's basically the ideal ranking for any particular query. No system can ever get a DCG better than that. So since that's the best DCG achievable for that particular query, I take the actually achieved DCG and divide by the ideal DCG to get the normalized DCG for a particular query at a particular rank. And kind of, as you can guess, this is going to be between 0 and 1. 0 if you're hopeless, and if you've done something that matches the ideal gain vector, then you get an NDCG of 1. And now, because kind of for every query, because the NDCG lies between 0 and 1, I can now average NDCG values across my 50 or 100 queries in the test collection. Okay, well, there's really more to talk about evaluation, but kind of, I think by now kind of map, NDCG, and P at K, these are the three things that you are likely to come across if you're kind of reading papers on this subject. So I'll stop with the evaluation part there. How much patience do you have now? I mean, I want to talk a little bit about query expansion, which is basically kind of, so far we've put together techniques for basic indexing, basic term weighting, and therefore basic retrieval, and how to kind of assign a score to how different term weighting schemes are doing, or in general, how different indexing schemes, how different retrieval schemes, how well they're doing. If you want to compare them, we have that machinery also available to us. Last thing that I wanted to talk about is kind of one of the techniques that's commonly used, at least in academic research, to improve search results. So kind of, how much patience would you have for that?
Yes, sir, you can continue.
Okay, so kind of, okay, let's see. So I'll get started anytime you think you've kind of had enough for one afternoon and evening. Just kind of, it's all right. I won't be offended. You can just unmute your mic and say it's evening and we want to go elsewhere. So the last topic we'll talk about is, as I said, kind of one method that is commonly used in at least academic research to improve search performance. So kind of, let's start by looking at kind of what's one of the obvious reasons why search results are not always what kind of as good as we want them to be. So one of the very common problems is what's called vocabulary mismatch. So vocabulary mismatch basically means that when I, as a user, when I want information about a particular subject, I am thinking of certain keywords. Whereas the author of a useful document, when she was writing the document, she may have been discussing the same subject, but she may have been using different terminology. So any search system that relies purely on keyword matching is bound to kind of fail to retrieve such documents. So it kind of, here's a very simple example. Suppose I am interested in statistics about casualties in traffic accidents. So I'm basically kind of say looking at news articles related to traffic accidents for say the past 10 years and trying to collect statistics. So if I have, assuming of course that somebody does not already have the ready-made statistics compiled for this. So if I am looking for information on this, then a news article that says 4 people were injured when a truck collided with a car or something, that's a relevant document. But notice that at the keyword level, there's no overlap at all. So even though our knowledge of the language says that this is a relevant document, because the systems that we have described so far are purely based on keyword matching, they fail to retrieve such relevant documents. What's an obvious fix? If kind of like as users, we don't want to spend too much effort. So kind of typical query that you submit to a search engine is usually what, like 3, 4, 5. Sometimes you're looking for a particular error message that you received when kind of maybe, I don't know, running some software or compiling some program. Maybe you kind of copy paste the whole message into your search box. But kind of typical queries are very often kind of 3, 4 small number of words. So if we could somehow take the query provided by a user and add more related words to it, so hence the term query expansion. So I given a small query, I expand it, I make it into a bigger query that has many more related keywords, then the chance that my system would be able to match relevant documents like this that use, say, synonyms or other related terminology, that chance I basically want to improve. So that's basically the kind of essential idea behind query expansion. So let's see. What I'll do is, because we have looked at 2 ways of computing term weights, so just quickly remind yourselves what those are. One was entirely heuristic. We just kind of depend on our intuition that tells us that high TF means high term weight, high IDF means high term weight, and long document length means low term weight. So from that, we got a kind of TF into IDF divided by document length kind of heuristic term weight, which we call the vector space model. The other term weighting formula that we derived was using that ball and urn model. And using that, we also kind of obtained a different term weighting formula that uses the same ingredients, but kind of arithmetic wise, it's a little different. So what I'll do is I'll quickly talk about query expansion methods that are commonly used by, say, these 2 schools of thought, if you will. So one query expansion method that was developed by the same people who proposed the vector space model, and then another query expansion method that was developed by the people who kind of proposed the language modeling approach to IR. Again, anytime you think you've had enough, just unmute your mic and say stop. Okay, so here's the engineering approach to query expansion. So it's kind of like you have a query, you give it to IR system, you get ranked documents. And now what I want is I want the user to give me feedback about which of these documents were useful and which of them were not. So at least give me some additional guidance on kind of what kind of documents you're looking for. If you can provide that kind of feedback, so that's what's technically called relevance feedback. If you can give the system that information, then you've kind of, in a sense, I mean, you've probably all done some kind of classification or the other in the past. So in some sense, you've given it some additional training data that says that these are the good documents, these are the bad documents. So the system is expected to use this training data to learn a better query representation, and kind of that's what we will get. Kind of the improved query representation is resubmitted to the system, and hopefully you kind of the second time around, hopefully you get better results. Okay, so here's the scheme then. So you provide a short query. The system retrieves some number of documents and maybe gives you some 4, 5, 10, whatever you have patience for. And you provide feedback about which documents were useful, which documents were not useful. And the system uses this feedback to learn a better query. Okay, what concretely does learning a better query consist of? Basically, words that occur frequently in relevant documents, especially when compared to non-relevant documents, these are the words that I should add to my query. And if the original query contains words that are not very discriminatory or bad in the sense that they occur more frequently in non-relevant than in relevant documents, then I want to eliminate or de-emphasize those words. So this kind of adding more words to the query and kind of tweaking the query term weights, that's basically what relevance feedback is intended to achieve. So what's the first or the oldest, most traditional method for relevance feedback? As I said, it was developed by the people who proposed the vector space model, and it's called Rocchio's relevance feedback algorithm. And kind of pictorially, the idea is something like this. Remember, kind of very early on, we started by thinking of a document collection as a term document matrix. And I said that kind of each document was basically, it's a row in a matrix. So you can think of it as a vector in an m-dimensional space where m is the size of your vocabulary. And kind of if you're with the vector space model, then you're using some kind of inner product or cosine similarity. So in some sense, kind of you can think of your query as a vector in that m-dimensional space. You have some useful documents, you have some non-useful or non-relevant documents. This is where your query was. What you want is, and kind of the nearness is reflected in the similarity scores. So this was the original query, some useful documents, but also a number of non-relevant documents close to the query. If you give me a few samples and I can change the query vector so that it moves here, and now it's closer to many more relevant documents away from the non-relevant documents, then this query is expected to give me back better search results. Okay, is everybody with me so far?
Yes, sir.
Okay. Is Shurupendra still here? Is there a session after this?
Well, sir, there is a session, but sir, we just now discussed.
Yes, Mandar, I am here.
Oh,
Suman here.
Sumanda, when do you want to start?
After you finish, no problem. I will wait for you.
I don't want to put everybody to sleep. Then you won't have anybody to talk to.
No, it's okay.
Okay, so it's 6 o'clock by my desktop. So maybe quickly in another, say 15 minutes, I'll try to wrap up. And if you talk about word embeddings, then maybe kind of I'll provide a cue for that also.
Okay, no problem. Whatever you suggest.
Okay. So I'll finish the discussion on Rocchio's algorithm, and then kind of give the pointer to the next lecture that you're going to hear. Okay, so here's the idea. We have, as I said, kind of the objective behind Rocchio's relevance feedback algorithm is to take the original query vector and use that to construct a new query vector that is closer to the relevant documents and further away from the non-relevant documents. Okay, so kind of this is what I want to do intuitively. How can I make it a little concrete? So suppose I concretize this intuition into the following principle. What I want to do is I want my new query to be close to relevant documents, away from non-relevant documents. Close to in what sense? Close to in terms of query document similarity sense. So if I compute the average similarity with the relevant documents here and the average similarity with the non-relevant documents here, a good query should have a high average similarity for relevant and low average similarity for non-relevant documents. So basically, I want to maximize the difference between average similarities for relevant and non-relevant documents. Okay, so let's look at kind of, now that I have an actual quantity to work with, let's write down the mathematical expression for this quantity. So the first term here is kind of, I look at all the relevant documents, look at their similarity scores, and take the average. I do the same for non-relevant documents and take the difference. So I have, this is the expression that I'm starting with. This is the expression I want to maximize. Now in the vector space model, the similarity score is given by the inner product. So basically, instead of sim q di, what I can write here is the vector representation of the query dot product di, or the vector representation of di. That gives me the similarity score over here. So now if I replace the similarity scores by the dot product and just take the dot product common, then what I get is this expression is nothing but take the average vector of the relevant documents minus the average vector of the non-relevant documents. So that difference is also a vector. And the dot product of that difference vector with the query vector gives me the difference that I want to maximize. Now, because it is a dot product that I want to maximize, when will my dot product be maximum? If this vector is parallel to this vector. So the dot products are minimum when vectors are orthogonal, you get 0. If the vectors are parallel for two given vectors, that is when their inner product similarity is maximum. So basically, if I were somehow, as in if the retrieval system were somehow omniscient and knew in advance for a particular query what the relevant documents are and what the non-relevant documents are, then the perfect query in this sense would be easy to construct. I would take the average of the relevant document vectors, subtract the average of the non-relevant vectors, and that if I just send that as my query, then that will be the query that maximizes this difference. But clearly, if I know in advance my complete set of relevant documents and complete set of non-relevant documents, I wouldn't have to do a retrieval at all. So basically, I am have to work with some representative relevant documents, some non-representative non-relevant documents. So in practice, what I do is the user has given me feedback and told me some documents are relevant. I take their centroid. I take the centroid of similar non-relevant documents, and I take a combination of some parameterized combination of the original query, the centroid of the relevant documents, and the centroid of the non-relevant documents. Okay. Now, basically around this simple idea, there are a number of practical issues that that you need to work out. Just like it's similar in some sense to the sort of engineering that we've already considered when we were looking at different term weighting formulae. All the TF factors are monotonically increasing factors of TF, but what I remarked was that depending on what actual function you use, your performance could change quite a bit. So it's the same thing over here. The general idea is simple enough, but the actual details that go into engineering a system that uses Rokio relevance feedback. There are a few issues to be aware of. Okay, maybe, I mean, because we don't have much time, maybe I'll spend a little bit of time talking on kind of possibly the most important issue that you should be worried about if you are doing Rokio relevance feedback in an operational setting. So that issue is the following. Go back to the original Rokio relevance feedback equation. So the three components are parameter tuning. That is something that you're all familiar with, so I won't talk about that too much. But the three other main ingredients are original query, relevant documents that the user has told me about, and non-relevant documents that the user has told me about. Now, kind of one practical thing to keep in mind is that for any given query, usually the number of relevant documents will be relatively small, whereas the number of non-relevant documents will be relatively large. So what I mean is, suppose you are doing a search for documents for a given for a query, and your document collection contains, say, 1 million documents. For most reasonable queries, interesting queries, the number of useful documents will be what? Kind of maybe 20, 30, 50, a few hundreds, maybe a few thousands. Remember, the document collection that we are working with will typically have hundreds of thousands, possibly several millions. So if you look at the number of relevant documents in comparison to the size of the collection as a whole, it's fairly small. So the 4 or 5 documents that the user told me that, okay, these are the documents that are useful, in some sense, they are much more representative of the 50 or 100 or 500 useful documents that are there in my collection. Whereas the non-relevant documents here, they are what? I mean, there are some handful of non-relevant documents from the several 100,000 non-relevant documents in my collection. So kind of this is going to be usually far more, I mean, the known relevant documents are going to be much more representative of all relevant documents than the few non-relevant documents that the user has explicitly marked as being non-relevant. What lesson do we learn from that? It's kind of, again, reuse of an old idea. This is a relatively decent sample. So any statistics that I compute over here are comparatively reliable. Over here, I shouldn't really be relying on any statistics computed from some 3 or 4 or 5 documents, because the total collection of non-relevant documents is very large. What can I do then? Instead of considering only the handful of documents that the user has explicitly marked non-relevant for this part of the equation, one simple thing that I can do is whatever statistics I need to calculate over here, I can calculate over the entire collection. Why does that make sense? Remember, I have a collection of 1 million documents, out of which maybe only 1,000 are relevant for this query. So whether I compute my statistics for non-relevant documents using all 1 million or 1,000 less than 1 million, my statistical estimates are not going to be very different. So kind of the operational point that this equation does not make clear is that very often it's, or instead of very often, I would say usually, it is much safer to use all the documents in the collection that are not known to be relevant as representative, not relevant documents, rather than only the 3, 4, 5, 10, whatever, however many small number of documents that are explicitly marked as non-relevant by a user. So again, there are kind of refinements on this idea. You can kind of look at this if you're interested, but we won't have time to discuss that right now. I think the last thing that I want to talk about in this connection is, so kind of, you might be a little disappointed in that kind of I'm expecting, in order to improve such results, I'm expecting you to invest much more effort than you usually do. So first you'll have to supply a query, then you'll have to look at the first 5 or 10 results, then you'll have to tell the system what's good, what's not. Who has time for all this? So even though relevance feedback is kind of effective, it's not very practical. So one kind of very cheap alternative to relevance feedback that turns out to be surprisingly effective on average is what's called, I mean, it's given different names. It's sometimes called blind relevance feedback, sometimes called pseudo-relevance feedback. And the idea is exactly the same as what we discussed so far, except that because you cannot expect in practice a user will take the time and trouble to give you feedback about the first 5 or 10 documents, you make the simplifying assumption that the first 5 documents that I retrieved, if I'm doing a reasonable job, they must all have been relevant. And if you do that, and if kind of some or most of the documents in the top 5 were actually relevant, you end up, and kind of you use old Rokio relevance feedback overall idea with this kind of assumed relevance rather than actual relevance feedback provided by a user. You also end up adding useful terms to the query, usually. So kind of, if you have a reasonable system to start with, and you do this kind of automatic feedback, retrieve top 5 or top 10, assume that they are relevant, and use the terms in those top 5 or top 10 documents to expand the query, then what you are going to observe is that next time, the kind of, you've already looked at the first 5 or 10, the next several documents that you look at will hopefully be more useful than they would be if you just use the original short query. One obvious risk, hopefully all of you are thinking about that also, that if the initial retrieval is poor and I get kind of out of the 5, maybe I get all 5 non-relevant, maybe I get only 1 relevant, 4 non-relevant, and then I make this dangerous assumption that all 5 are relevant and do feedback, then of course my second round results are going to be even worse. And kind of that's true enough, that is actually what's observed in practice also. So you can think of this kind of blind feedback or pseudo-relevance feedback as a kind of risky game. If you've done a reasonable initial job, second round you'll get better. If you did a bad job initially, second round will be much worse. So what people have observed, I mean, the reason why I'm saying this is kind of probably more of academic research interest than in practical systems, is that in practice, for the question papers that are used to evaluate practical IR systems, and remember question papers, I'm talking about query collections of 50 or 100 documents. In the actual benchmark collections, exactly this is observed. For some queries, performance improves quite a bit. For other queries, performance degrades. But on average, the average overall performance increases quite a bit for kind of the usual set of 50 or 100 queries that are used in standard benchmarks. Okay, so there kind of there was lots more material on query expansion in these slides, and kind of the slides are available with you. There's also some references at the end that you can use for further reading. I'm hoping the Winter School homepage will also have my email address. So if you need additional references or have any kind of questions, you're always welcome to write. But kind of before I close, I'll just kind of introduce a quick idea that will hopefully kind of tie in well with the next set of lectures that you'll be attending. And that's kind of the following. Remember, the whole idea behind query expansion was, given a short query, there's the risk of vocabulary mismatch. So I want to somehow expand the query with related words. So the technique that we looked at, procure relevance feedback, is basically depending on the user to provide some inputs that we are going to use in order to find additional words related to the query. A completely different method would make use of kind of word embeddings. Kind of quick show of hands, please. Can kind of if word embeddings are something that you're familiar with, and chances are kind of pretty much everybody seems to be familiar with embeddings these days. Can you do a quick raise hand? Okay, so there were 2 raised hands, which I'm a little surprised. I mean, pretty much everybody seems to know about embeddings these days. So I think that's good for Shumanda, who will be talking about word embeddings next. So I think the idea there is that kind of what you learn about word embeddings gives you a more direct way of kind of, given a particular word, find other words that are related to this given word. And as you can imagine, if you have such a tool, think of it as something like an automatic thesaurus. Given one word, find other words that are related to this word. If you have such a tool, intuition suggests that it should be a very powerful tool for query expansion. So kind of, I'll leave it at that by way of introduction to the next set of lectures, but kind of just one small additional clarification that as we've kind of encountered on a number of occasions so far, an idea that is intuitively appealing does not always turn out to work well in practice. So kind of that, I think that has been the case so far with embedding based query expansion methods, at least as far as plain straightforward document retrieval is concerned. So kind of, if you are looking for interesting projects where you might be able to make a difference, you could look at using word embeddings for query expansion. Somehow the potential that they seem to have, I don't think that has been achieved yet. So that would be one possible area where you can kind of explore stuff. Okay, so I'm kind of 20 minutes over time. So I'll stop here. As I said, kind of any questions, please mail me. If you need additional material or references, I can provide that as well. Okay, that's it. Thanks for your patience. And it's over to Shumanda. I think he'll also probably give you a quick break before he gets started on word embeddings.
Thank you, sir.
Okay, I'll stop my share and then Shumanda can go ahead with. Okay, so Shumanda, may I sign out now and then kind of you can take over after a quick break?
Yes, no problem. Whatever, because I think Prasenjit and Sandeep, they are the chief. So whatever they will say, I will go by that. No problem.
Okay.
Thank you, sir. Thank you, Mandar, sir.
Okay. Thank you, Sandeep bhai. Okay. I leave now. Then any follow-up questions we can take them off.
So, Supendu, can we take 5-minute break or 2 minutes? What do you suggest?
I think 5 minutes break.
So
5 minutes break is okay.
We all assemble at 6:25, I suppose.
Yeah, and then sir can start his lecture.
Okay. Sir, Suman sir, 5 minutes. Just.
Okay, no problem, no problem. I'm here, no problem. Whatever you decide. So meanwhile, can I check my screen sharing?
Yeah, sure, sir. Sure.
You are co-host.
That is better, I think.
Yeah.
Let us see. Because I say share.
Sir, it is visible.
It is visible?
Yes, both are visible, sir. Your board is also visible and your PPT is also visible.
Oh, great. Thank you. So from where do I go and stop?
Sir, at the top, if you go on the top of your screen, if you just take the mouse, you should get a drop down sort of thing. You have to take the mouse to the top of the screen, of your own screen. Yeah. Do you see a drop down? Yeah, that's a meeting control, something like that.
I stop, right?
Yes.
It's okay now?
Yes, sir. Yes.
Great. I participated in Zoom meeting, but not shared or not given any lecture in the Zoom.
Yeah. Zoom, sir, it's the most popular tool, online platform tool, actually.
Oh,
But, we use generally Google Meet. Even I use Google Meet or something. But that's true, sir. You are right.
Yeah, it's okay. Almost similar kind of a feature most of the time in most of the platform. Something here and there.
But this Zoom gives, additional feature like host, co-host. So, you can, create more custom. You can customize your meetings.
Okay.
And this from the sir, just on a different note, from the Wall Street listed company, the Zoom is the biggest beneficiary of the pandemic.
Oh, is it?
So this IT company are beneficiary, but Zoom is the biggest beneficiary. It's value multiply 10 times within 6 or 8 months.
But are we paying something to Zoom?
Yes, sir. It's we bought from Professor Majumdar's on behalf of Prasenjit Majumdar's he bought the license version of the Zoom.
Okay.
And there are two variants. One is a webinar and one is this meeting. So
Okay.
But no, sir, Zoom is only doing this video conferencing. This is their core business. But Google and WebEx, they have so many.
They have some other businesses also, right?
And Zoom is only doing this conferencing.
Right. Oh, I see. It was bought for Fire 2020. Okay.
Yes. So, Surpendu, can we start?
Yes. Yeah, it's 6:25 already. Yes.
Okay.
So, sir can start.
I should make myself visible for the few minutes.
Okay.
Should I start?
Yes, sir.
Okay.
Yes.
Okay. So, good afternoon, everyone. Rather, good evening. So, I hope you are not too much exhausted. I will not tax you today too much. I will go on giving some overview of the word embedding, little bit of history, why, how, etc. And then in tomorrow's talk, what I will be doing is that I will be going little bit into the deeper of some of the recent word embedding techniques. And then I will little bit talk about some of the work that we are engaged in with word embedding for the Gujarati language. So now let me start telling you is that, okay, let me share my screen first. Can you see my screen?
Yes, sir.
Yes, sir.
I have two screens. One is my whiteboard. Another one is my PPT. Is it okay? Okay, so I'm working in Dhirubhai Ambani Institute of Information and Communication Technology at Gandhinagar. And so this side of the top left side is the logo of DAIICT that I am putting. And we have a small group within Dhirubhai Ambani Institute. We called it a Center for Artificial Intelligence and Language Processing, whose symbol is on the top right corner. Here it is, AILP, Artificial Intelligence and Language Processing. I basically, by training, is a statistician. Then I did my PhD from Indian Statistical Institute in the area of image processing and pattern recognition. So I am practicing pattern recognition for a long time. And very recently, for last almost 2-3 years, I'm getting into the field of natural language processing and restricting myself mostly towards word embedding, and that is towards the low resource language word embedding. Mostly I'm considering Gujarati in place for my word embeddings. So today and tomorrow, I will be talking mostly about the history and genesis, and then how the word embeddings unfolded into the researchers that I will talk about. I will little talk about the application areas, that is Gujarati word embedding and some Gujarati news classification problem, which used already the word embeddings, Gujarati and non-Gujarati word embedding also, right? And on the Monday schedule, which is with me, the TAs, mostly Sriparna, will be telling you that hands-on about how to do word embedding, particularly how to implement it in the lab on the real corpus. Sriparna will help us to understand that one, and Professor Mehta and others will also join to assist. So basically, I will start with a little bit of history and little bit of recent development or recent talking about the word embedding problems, as well as in general the challenges in natural language processing. So if I go back to the history, natural language processing research mostly started in 1950s. So it has a long history. It is not a very recent one. So it has a history of almost 70 years that people are actually working on the natural language processing. So very obvious that it started with natural language processing in English language, and then slowly it's built up and get into the other languages also, mostly the Russian, European languages, etc. Then come to the Asian languages and so on and so forth. And there are various challenges and different challenges for different languages that if you start working on that one, or those who are already working on that, they can understand very easily that the language, if you are doing on a vertical, for example, say some Indian languages, Hindi, Urdu, or anything else similar to that one, Gujarati, Bengali, Tamil, etc. It has their own challenges also. Or we may, time to time, as I remember, I will give you some hint about the challenges of the local languages. But what is the most important? Can I actually stop my video? Just a minute. How can I, Sandeep, I have little bandwidth problem. How can I stop my video?
Sir, I off your video.
Okay, 1 minute, sir. We will.
You will do it?
Yes, yes.
Okay, okay, great. So basically what I'm saying is that I'm recently looking at some papers which are telling that what are the very recent challenges in the natural language domain. So they are saying that one of the most important challenge that we have is understanding the contextual meaning of the word or sentences. Because you see, lots of work are going on in the sentiment analysis for social media, right? So big companies, they are doing that for increasing their business, understanding their customers, etc. And in some other areas, people are also trying to analyze the sentiment of the tweet, sentiment of the Facebook, sentiment of WhatsApp, or whatever it is in the social media, so that they understand the overall trend. The political parties are not exception of this. They are also trying to do sentiment analysis in the social media to understand the people's mind so that they can manipulate and they can make the proper manifesto to actually capture the attention of the people. So that means that there are a lot of scopes and it is still going on and it will be on for next few years, that sentiment analysis in the social media. But the problem is that that particular area of NLP is still lagging in understanding the proper sense of the sentiment due to the problem of words having more than one meaning, or the sentences having more than one meaning. For example, whether a particular sentence is said in the context of surprise or in the context of sarcasm, or it is irrelevant of anything that we may not be knowing. For example, suppose someone says, "Is it so?" Now, depending on what the meaning is it so, only the text remains same. Maybe somebody is very surprised and asking this question, or surprisingly say, "Is it so?" Or maybe someone is very sarcastically saying, "Is it so?" Do you understand? So it is not the conversation. It is only the tweet or text coming out. So the text is same. Is it so? Now, is it so is what? Is it a sarcastic statement, or it's a questionnaire kind of a statement, or is it a surprise kind of a statement, or what? We do not know right now. That is the challenge. That is the main challenge that context-wise, can we understand the sentiment? And word embedding, a very sophisticated kind of a word embedding is required to understand the context of the word or the embedding of the word in the context. That is still elusive. Still we are not getting into that area. Do you understand this? Sometimes you be with me, otherwise I will feel that I am talking to nobody. Right?
Yes,
do you
sir.
agree with me?
Sir, yes, sir.
That the whatever we do, the word embedding or whatever, but still context is very important. And that solution is still elusive. That we are not finding the context properly in many of the cases. Professor Sandeep Moda is present over here. He is a veteran in sentiment analysis, fake news, etc. He can tell us in a better way that context, the same word, same sentence may have a different meaning in different contexts. So capturing that is a big challenge in the coming years. And word embeddings, specifically, a very robust kind of word embedding is required to actually capture that one, right? Now, another problem is that, I'm not saying problem because it's a challenge. The challenge is actually the multilingual sense. So one challenge I said that NLP still struggles with conflation deficiency. That means trying to capture more than one meaning of word or sentences. Now, the second thing is that multilingual NLP, because this is a big challenge. Though English is the most popular speaking language or most popular language by which we communicate to each other, today also we are talking in English. But still, multilingual NLP is going to be a big challenge because of the spoken persons available in the European region, in the Indian subcontinent region, and in some other region also. Though actually what I'm saying is that big companies such as Microsoft, Facebook, they are trying to build up this multilingual model. Have you heard the model by Microsoft called Turing model or Turing model, Turing, Turing model? Have you heard that one?
No, sir.
Okay, so today after the talk, you may actually try to Google the word that Turing model by Microsoft, right? And there is another model called M2M model, capital M, number 2, capital M, dash 100, M2M 100 model by Facebook. So what they are doing is that in the Turing multilingual language model incorporates information theoretic framework for a cross-lingual language model. It's a huge work by Microsoft. They are representing 94 languages and putting into the same vector space. I hope now you have some idea about the vector space, because we are 3-4 days veteran in the NLP Winter School. So I know, can I assume that you know vector space model? That means you are putting text and everything into a vector, and that vector space is being analyzed, right? So what they are doing is that they are taking 94 different languages and putting into the same vector space for analysis. So this is really a very good work by Microsoft, which is called Turing model for the multilingual NLP. And in the M2M100 model by Facebook, you know, they are considering 2,200 languages and can directly translate any pair of 100 languages without using English data. Without using English data. That is the most important part of M2M model. M2M model. So that is another very challenging thing that we have is the multilingual. And for that, word embedding possibly plays one of the major and important role for natural language processing in multilingual natural processing. Because you see, I am not very sure because I cannot give you the answer right now. People are working on it and it will take a long time to understand whether the same word embedding model will work for all the languages or whether a unique word embedding model can be operated on a large number of languages. Whether that is possible or not, I do not know. May be possible, may not be possible. Only research in the future will tell us whether that is possible or not possible. Okay? So with this introduction, what I would like to tell you is that we have the agenda for our talk in this winter school is that what is word embedding, how is it important, different embedding techniques, and embedding in low resource language. That will come at the end. Okay? So let us first look at what are word embedding. By the way, I hope many of you are researchers in the NLP areas. They may be knowing many things of the word embedding. So my lecture is not targeting to those who are already veteran in the NLP areas. I give it a basic thing so that those who are at the starting point, those who would like to start, they can have some idea what is this, what is that we are doing. But I am not saying that those who are already experienced in the natural language processing area, they may not get anything new. They may. I am not very sure because I am also a learner in the word embedding world. So in simplest thing, word embedding is a model. What it models? It maps the textual data to vectors of real numbers. So if I take the scenario, it will be like this. It will be exactly like this. So what we have over here is a collection of words, right? W1, W2, W3, Wn, etc. Collection of words. Now, how this collection of words are collected, I'm not going into the detail right now. Only I'm saying that what is the model. So this is the model. This is here, the model is. This model maps these words into a vector space. So I draw over here a 3-dimensional space. It could be a 2-dimensional space, 4-dimensional space, or n-dimensional space also. So that means word 1 over here is given by this vector W1. Word 2 is given here by the vector W2. Word 3 is here given by this vector W3 and this one. Right? So this is the main meaning of word embedding. That we have words, we have to use some model so that word can be embedded or word can be put it into the vector space, into the space of n-dimensional vector. N could be 2, 3, 4, 5, etc. Right? Then what will happen? Then it will be easier to model and use mathematically, because now I have the words in the form of a mathematical formulation, that is a vector. That is vector. So word is going into the vector. So word going into the vector. So if word is going into the vector, I can mostly use it for the mathematical modeling. And there is clear-cut use of this modeling in current days into the deep learning era. Now, what I'm trying to tell you is very important. Like many other AI field, natural language processing or natural language modeling is getting into two distinct era. One is pre-deep learning convolution neural network era and post-deep learning convolution neural network area. No model of this word embedding is actually in between these two. Either it is pre-DL era or post-DL era. I will tell you the history and chronology of the word embedding, so you will understand from there that how it actually changes from the pre-deep learning era to the post-deep learning era. But nowadays, as we are talking about, it is mostly the DL1 that we are focusing on to model. So this word embedding model, taking word to the vector, is most important thing to understand. Right? So I'm coming back to my slide. So it is the meaning. So now the most important part. The mapping is done not heuristically. The mapping is done in such a way that one or all of the following properties hold. This is very, very important part as far as word embedding is considered. Morphological structure of the word should be preserved. Contextual representation of the word should be kept. Relationship of text within a certain set of documents should be kept. So if I allowed to give, or if I am to give one or two examples of each one of these, let me try this way. So what is the morphological structure of the word? The morphological structure of the word is that some kind of modifier is added into the word, though the meaning should not be changing drastically. For example, walk and walking. So the meaning is not changing drastically. We are understanding that the word is trying to say that somebody or someone or something is walking or walks or whatever, right? So it is connected to the term walk. Though a modifier ing is added into it and we called walking. A modifier ed is used, so we called walked, something like that, right? So in the mapping, word embedding mapping, the term walk and the term walking should not be far apart. They should be little bit closer in the mapping. That is the first one, morphological structure of the words. Second is contextual representation of the words. So what is the contextual representation of the word? The contextual representation of the word, Suppose I say long live. How do you complete this sentence? Long live. Can anyone tell me? If I say long live and I pause, what will come next? Huh? Yes, tell me. Whatever coming in mind, you tell me. So, you see, most of the time we say long live king, long live queen, long live prime minister, long live president, something like that, right? So, a designation which is very important. So, that is my contextual representation. That contextual representation means that it should be something which is mostly related. That should be again close to each other, right? Close to each other. Another example is that if I say that man is equal, that is okay, let me take the very famous example in word embedding. They said that what will happen? Man plus king minus queen equal to what? So one side we have man, king, another side we have queen. So we must have the remaining word by woman. Right? Woman. So that is the contextual representation. Contextual representation. Right? So it should be like that one. So they should not be very far apart in the embedding, into the mapping. Right? That is the concept. So if we have distance between man and king will be similarly distance between woman and queen. Right? Or say distance between man and woman has the same distance between king and queen. Something like that. Right? So all these are contextual representation of words. And then relationship of text within a certain set of documents is that, suppose I said cat, dog, horse, house. So what is that? So you see the first three terms, cat, dog, horse, are set of animals. So they are some way related. But if we take house, house is not related with that one. So house is little bit apart from this kind of words, cat, dog, horse, etc. Right? So that is what is called the word embedding. So I have put some example of it. I have already given you the examples. So in this following image, what we are saying is that this is what? King and queen is actually equivalent to man and woman. So king, man, woman, queen, all these words are embedded in such a way some kind of distance relation is preserved. Some kind of distance relation is preserved. Again, I already told you, walking and walked, swimming and swam. Some kind of distance between this pair of words should be preserved. So the first example is male-female kind of relation. Second one is verb and tense kind of a relation. And then another kind of could be something like this, country and capital. So Spain, Madrid, Italy, Rome, Germany, Berlin, etc. Right? So in embedding, we should be doing in such a way so that if we say that Spain plus Madrid minus Italy, it should be equal to Rome. Right? So this kind of a distance in between the words should be preserved. Right? So we are showing that how embedding preserves the contextual relationship amongst them. Okay? And this particular image I have taken from this particular website. It's a blog. From there I have taken. Whenever I have taken some picture or something, I have already made the acknowledgement for that. Now, the meaning that I was telling you is that the word embedding. So how we are getting embedding? Because if you look at my whiteboard, so what we said is that, so this here we have nothing but text, but here we have a three-dimensional vector. So W1 is W11, W12, W13. That is my W1 equal to either a row vector or maybe a column vector, whatever you decide, right? Maybe a column vector. So this is a column vector, means this is numerical. This is not textual. So that means the word embedding implies that from text to this numerical we have to find out. So how to do that one is the question that we will be asking for our lecture. So I'm giving again a little bit example. The example is taken from another website. So something like this. Word embedding represents word into vectors of real valued numbers in another vector space. That is already I shown you through that picture. Each word is associated with a point in vector space. That is also I have shown you through my whiteboard. The vector space can be of any dimension. That is very, very important. For example, in this particular figure, what we are showing is that cat, kitten, dog, houses, man, woman, king, queen, all are actually a 7-dimensional vector. What these vectors are? Because living being, feeling, human, gender, royalty, verb, plural, etc. So these are the component of the vectors by which we are putting. So whenever we see cat, cat is represented by this vector, which is a 7-dimensional vector, saying the first value is 0.6, second value is 0.9, then 0.1, then 0.4, then minus 0.7, then minus 0.3, then minus 0.2, right? But I am not showing this particular 7-dimensional vector into the vector space. Instead of that, I am showing only a 2-dimensional vector space. I am only showing a 2-dimensional vector space. So dog, cat, kitten, houses. Now you see, cat and kitten are very close to each other. So that is the meaning of embedding. That means some kind of relationship is existing also in the embedding. So cat and kitten are close to each other. Dog is not far off, but moderately far off. Why moderately far off? Because dog obviously is not cat and kitten, but if we consider the animal, then they will be closer to each other, right? But if you see houses, which is far apart from all this, because that is a non-living thing, houses. Okay? So there is a big scope of research even in the word embedding, which is called dimensionality reduction. Dimensionality reduction. In this particular example, dimensionality reduction takes place from 7-dimensional to 2-dimensional. So dimensionality reduction is also playing an important role in word embedding also, right? So any one of you know the dimensional reduction technique? Any dimensional reduction technique? Any one of you? Hello? Somebody said something.
So filters are used for dimension reduction, like random forest and
No.
Principal component analysis.
Principal component. Random forest and all those are not dimensional reduction technique. Those are what? Those are classifier. We are not talking about the classifier. We are only talking about the dimensionality reduction so that the properties are still hold good. The information present in the higher dimension should also be present in the lower dimension. Whatever information I am revealing with this 7-dimensional vector, the same is revealing over here in the 2-dimensional vector. That is cat, right? So principal component analysis is a very important dimensional reduction technique that is taking place in the word embedding field also. So principal component analysis is a tool for machine learning for dimensional reduction. So you can look at that one. And there are many other sophisticated and more recently developed dimensional reduction. We have also worked on many of the dimensional reduction techniques. One of them is very important, called locality preserving projection. Locality preserving projection. So that's a very, very important one. What is locality preserving projection? It says that if two vectors which are close to each other in their original space, they must be close in the projected space. So exactly the same thing what I am showing in this figure. This figure is shown that cat and kitten, if you take the distance between cat and kitten, they are close to each other compared to any other distance like cat and dog, cat and horse, in this cat and houses, in this 7-dimensional space. So cat and kitten must be also very close in the lower dimensional, that is 2-dimensional space. So by this way, one can use the locality preserving projection for the dimensional reduction of word embedding. This locality preserving projection for last 5-6 years, we have actually worked out with various versions of locality preserving projection called the extended locality preserving projection, then orthogonal locality preserving projection, etc. So you can look at and Google it and can find out. So in this particular talk, I'm not going into the dimensional reduction technique, but I'm only giving that as an example that why and how the 7-dimensional vector is actually projected into 2-dimensional vector. Similarly, here also man, woman, king, queen. So the distance between man and woman, king and queen must be preserved in the 2-dimensional space also. This way the dimensional reduction should be taken place. But I am giving you a caution. If you are using principal component analysis, it is not always true that this will happen. This will happen. Because principal component analysis is, what it is doing is that it is trying to find out the direction which is most variable or most varied. So there are 7. So out of these 7, they are trying to find out which is the most varying direction. And that direction is the most important or principal component. That is why the name comes principal component. And the subsequent dimension would be orthogonal to the first principal component. Right? This way. But what I said, locality preserving projection and their variations like extended locality preserving projection and so on, they do not use that one. They use the philosophy which I told you, that keeping the distance almost similar in the lower dimensional space. Okay? Why it is important, I already told you so many things. So many machine learning algorithms are incapable of dealing with plain text. That is very obvious because machine does not understand the language. Machine does not understand the text. It understands only the numerical values, right? So machine in particular, the computer understands only 2 numbers, 0 and 1. So somehow we have to put the text or word or whatever is plain text into some numerical values so that the machine can understand. And the input to these algorithms and deep learning architecture is required to be numbers. Again, same thing that I said that the post-deep learning era, it is required that deep learning will take the vectors or some numbers as input. So we have to have the plain text converted into numbers so that we can use it in deep learning. And what embedding does can be shown in the following figure. So we take raw text or strings, word embedding, real numbers required by machine learning algorithms or deep learning architecture and so on, right? So different types of embedding. So Sandeep, when should I stop? I can actually talk from this maybe tomorrow, because today it is already more than 7.
Yes, sir. You can. That's fine, sir. You can talk tomorrow also. No
Because
problem.
today it is already more than 7.
Yes, sir. Yes.
We can start tomorrow before 6, so that we can have one hour more time to actually talk about types of word embedding and then the chronology, history of word embedding, and discuss two most important architecture, and then take the example of low resource language modeling, that is Gujarati. Okay?
Okay. Thank you.
Okay.
So see you all. Okay, we see you tomorrow at 3 p.m. Thank you very much.
Yeah, before closing, yeah, sorry to interrupt like this, but before closing, for the participants, we have launched a poll in Zoom. So before you leave today, please fill that up. It has only 4 questions, and we want your feedback in that. If you see down, there will be a polling option. I hope everyone is able to see that.
On your screen, the polling option is
Yeah, I have launched the poll now. So yeah, I think I am already getting responses. Okay.
Something is happening, I can see.
Yes, sir. They are filling the feedback form actually.
So Shrupendu, Sandeep and others. So I will come back tomorrow at 5:30 or 5:45 so that we can start our session in time.
Yes, sir. Yes. Yes.
Great. So I stop sharing. No.